What could before the Big Bang mean? What is cosmic inflation? How did tiny fluctuations become galaxies? Imagine, for a moment, an unfathomable darkness before anything existed. No stars, no galaxies, not even a single breath of light. Nothing at all. Not even space or time as we know them. In this boundless nothingness, there is complete silence and stillness. It's almost impossible to picture, a state with no before and no after, because even time itself has yet to begin. In that endless, soundless void, there are no moments ticking by. Yet from this mysterious emptiness, our entire universe would one day be born. For centuries, human beings have gazed at the night sky and wondered how it all began. In ancient times, many believed the cosmos was eternal, or that it was crafted by divine hands out of nothing. It wasn't until the 20th century that scientists found convincing evidence the universe had a beginning, the event we call the Big Bang, nearly 14 billion years ago. Not all scientists were immediately convinced. For a time, some proposed that the universe had no beginning at all, a steady-state cosmos where new matter would continuously appear as space expanded. However, the discovery of a faint cosmic glow left over from an early hot phase, the cosmic microwave background, eventually confirmed that our universe did indeed erupt from a fiery infancy. But the question that lingers is perhaps even more profound. What, if anything, was happening before the Big Bang? It's a question that stretches our imagination to its limits. According to some physicists, the concept of before the Big Bang might not even make sense. Time itself, they say, began with that primordial explosion of space and energy. By this view, asking what came before the dawn of time is like trying to go north of the North Pole. It simply cannot be done. If time truly started at the Big Bang, then there was no before in any conventional sense. There was only a timeless void, without moments, without change. Time is so fundamental to our experience that imagining its absence is nearly impossible. If time truly began with the universe, then asking what came before is like asking what lies beyond the edge of existence. And yet, our curious minds can't help but explore the possibilities. Some scientists have dared to imagine scenarios in which something existed prior to the Big Bang. One idea envisions that our universe is just one cycle in an endless cosmic loop. In this cyclical universe, time and space could expand outward from a bang, then slow and contract back in a big crunch, only to rebound in another Big Bang, a phoenix rising from its own ashes, over and over again. If that is true, then our Big Bang may have been the rebirth of a universe that existed long before, repeating an eternal rhythm of creation and destruction. Another tantalizing theory suggests that our Big Bang was not a unique event at all, but one of countless others, popping off in a far larger reality. In this multiverse picture, there might be innumerable universes, like bubbles in a vast cosmic foam. Maybe our universe was born when one tiny bubble, a small pocket of space, suddenly expanded and inflated into everything we see today. If so, then before our Big Bang, there could have been other Big Bangs elsewhere, each giving rise to its own separate universe with its own story and its own laws. In the multiverse, time might stretch infinitely into the past and future, with Big Bangs happening here and there like bright fireworks in an endless night. Some thinkers go further, speculating about dimensions beyond our own. They picture giant cosmic membranes, brains, floating in a higher dimensional expanse. Every so often they imagine two of these brains might drift into each other and collide. The impact would release tremendous energy, creating an entire universe our universe in the aftermath. From within our perspective, it would look just like a big bang erupting out of nowhere, a sudden burst of creation from the void. But in this brain collision theory, there was indeed a before, a time when those membranes glided silently through a larger space until their fateful collision birthed the world we know. There are even exotic propositions, like the idea that our Big Bang created not just our universe, but a mirror version as well, an anti-universe that stretches out backwards in time, opposite to our own arrow of time. In that strange scenario, if we were to rewind the clock to the Big Bang and then keep going before, we wouldn't find nothingness, but rather another universe unfolding in reverse. It's a mind-bending thought that challenges everything we take for granted about time's one-way flow. As incredible as these ideas are, it's important to remember that we have no direct evidence of anything that came before the Big Bang. These are whispers and echoes of speculation at the very edges of science and imagination. The truth is, we may never be able to know for sure what preceded the birth of our cosmos. Will we ever know for certain what happened before that first moment? Perhaps not, but simply pondering it expands our sense of wonder and primes us for all the mysteries to come. The very beginning, the origin of time and space, lies behind a veil that today's physics cannot yet pierce. So we find ourselves in a peaceful kind of ignorance, standing at the shoreline of the knowable cosmos and peering into the fog of before. We contemplate a time when time itself might not have existed. We imagine universes cycling, colliding, or sprouting like foam on the sea of a larger reality. Each idea is a tentative candle in the dark, trying to illuminate a realm we cannot truly see. Whatever the reality might be, all of these possibilities converge on that mysterious moment nearly 14 billion years ago, when our universe sprang into being. In an unimaginable flash, the universe went from nothing, or perhaps from something unknown and unseen, to an immense, hot, brilliant state of energy and light. Space and time themselves began to unfurl. In fractions of a second, the newborn universe grew from smaller than an atom to something the size of a grapefruit, then larger and larger still. This was the Big Bang, the moment that marks the beginning of everything we know. From that first blinding flash, our cosmic story began. Space and time unfurled, energy cooled into matter, and the infant universe started to take shape. The deepest mysteries of before time remain unresolved, but pondering them has set the stage for everything that comes next. As the universe expanded and evolved, tiny irregularities, little seeds of future galaxies and stars, were sown in those first moments. It's to those primordial seeds of creation that we now turn our attention as our journey through cosmic origins continues. Picture the universe in its earliest moments, a newborn cosmos, smaller than a grain of sand, hotter and denser than anything we can imagine. In that infancy of creation, everything was in flux. The laws of quantum physics ruled this tiny realm, and nothing was perfectly still or uniform. Even in what might seem like a smooth, hot soup of energy, there were minute flickers, little random fluctuations popping in and out. It's as though the newborn universe were alive with tiny bursts of energy, momentary flickers that appeared and vanished almost instantaneously. These quantum fluctuations were like the faintest of whispers echoing through the young universe. Tiny imbalances, where one spot might have a touch more energy than another. In our everyday world, such small differences would hardly matter at all. But in the extreme conditions of the early universe, These tiny variations would end up making all the difference. In those first instants, the universe was so dense and fiery that it was opaque, a brilliant, glowing fog of particles and light all mixed together. Yet it was not perfectly even. It had slight unevenness, speckles of higher and lower density scattered throughout that primordial glow. They were incredibly subtle differences, perhaps only a few hundredths of a percent, mere tiny fractions. But they were there. Then, something extraordinary happened. A split second after the Big Bang, the universe underwent a sudden, exponential growth spurt. Scientists call this fleeting moment inflation. During inflation, space itself expanded at a mind-boggling rate, faster than light could normally travel, which is possible because it's space itself expanding, not objects moving through space. In far less than a blink of an eye, a fraction of a trillionth of a second, the universe swelled from microscopically small to astronomically large. Imagine all of the vast cosmos we know today compressed into a volume smaller than a marble, then rapidly ballooning outward. One moment, everything is compact beyond comprehension. The next, space is rushing outward in a torrential expansion, like a bud bursting into a gigantic bloom almost instantaneously. As space expanded so dramatically, those little quantum fluctuations, those slight differences in density, were stretched and magnified enormously. What had been microscopic irregularities were blown up to cosmic proportions. It's as if the tiny wrinkles in the fabric of space-time were suddenly ironed out into larger patterns. Regions that had just a touch more matter or energy became whole patches of the young universe that were denser than their surroundings, and places that had a touch less became vast zones that were a bit more empty. Inflation took the quantum seeds and planted them across the stretching cosmos. When that frantic burst of inflation finally settled, the universe continued to grow more slowly and began to cool. The raging flood of particles and light started to calm. During those early moments, the newborn cosmos even resonated with waves, cosmic sound rippling through the hot plasma, which would later help shape the pattern of matter. Eventually, after about 380,000 years, the universe cooled enough for the first atoms to form and for light to travel freely across space. We still see that ancient light today as a faint afterglow permeating the universe, the cosmic microwave background. This gentle glow is like the dim embers left from a cosmic fire, the heat of creation itself, now cooled and quiet after billions of years. If you look closely at that background glow, with sensitive instruments of course, you'll notice it isn't perfectly uniform. It has an intricate patchwork of slightly warmer and cooler spots, like a subtle celestial tapestry. If you could have witnessed the universe at that time, you would have seen a brilliant, foggy glimmer in every direction. It would have been nearly uniform, a white-hot haze across the sky, but not perfectly even. There were faint blotches and speckles where it was just a touch hotter or colder. Those patches are the direct imprint of the early fluctuations, the fingerprints of the quantum seeds. They show us how certain regions had a bit more energy and matter long ago, and others had a bit less. These slight differences meant that gravity now had something to work with. Gravity is the great sculptor of the cosmos. It pulls matter together. In a perfectly smooth universe, gravity would have nothing to latch onto. Everything would be the same everywhere, and nothing in particular would collapse into stars or galaxies. But our universe was not perfectly smooth. It had those tiny variations, those seeds of structure. In regions that were a little denser, gravity exerted a stronger pull. Over millions of years, those areas began to draw in more and more material from their surroundings. The rich got richer, so to speak. Dense spots grew denser, gathering mass, while emptier regions were left even emptier as matter flowed away toward the denser clumps. Slowly, as ages passed, the first stars ignited within these growing clumps of matter. For a long while after the Big Bang's initial flash faded, the cosmos was shrouded in darkness. No stars shone yet, only immense clouds of cooling hydrogen drifting through expanding space. Gravity was quietly at work in the background, gently pulling these gas clouds together into denser pockets. After hundreds of millions of years, those pockets became the cradles of the first stars. When those first stars finally ignited, they lit up the darkness of the young universe. Swarms of stars gathered into the first galaxies, and clusters of galaxies formed around even larger concentrations of mass. All of the magnificent structure we see in the universe today, every galaxy, every cluster, every swirling nebula, can trace its roots back to those tiny quantum irregularities in the very beginning. It's astonishing to realize that the grand design of the cosmos, the glittering tapestry of galaxies strewn across space, was seeded by subatomic fluctuations in a time before atoms even existed. It is almost beyond belief that such tiny, random flickers could ultimately shape the clustering of galaxies on a cosmic scale. The quantum seeds truly sparked everything. From almost imperceptible beginnings, they led to the vast cosmic web of structure that fills the universe. They were the little nudges that set matter on a path to collect and form stars and galaxies. The quantum seeds set the stage, but gravity and time were the artists that patiently drew out their influence. And as much as gravity and time were necessary to build this cosmic architecture, there was another ingredient at play as well. An unseen influence was helping shape the growth of those primordial clumps. While the newborn universe's ordinary matter and light were dancing to gravity's tune, a hidden form of matter, completely invisible, yet far more abundant, was also gathering and pulling, sculpting the universe in ways we are only beginning to understand. This invisible mass would be crucial in forming the scaffolding for galaxies and clusters. Our journey now turns to this mysterious substance, the hidden matter that holds the cosmos together. Drifting through the vastness of space is something profoundly mysterious. It's everywhere around us, yet we cannot see it or touch it. Astronomers call it dark matter, the hidden mass of the universe. Unlike the stars and planets, dark matter doesn't shine or reflect any light. It moves through space like a ghost, invisible and silent. You could be passing through a sea of dark matter at this very moment without ever knowing, for it interacts so faintly with the atoms of our bodies and our world. Indeed, as the Earth moves through the Milky Way's dark matter halo, countless invisible particles stream through us all the time, like a silent, imperceptible wind. And yet, despite its secrecy, dark matter's presence is felt across the cosmos through the gentle pull of its gravity. The story of dark matter began with a puzzle. In the mid-20th century, scientists observing galaxies noticed something strange about the way they moved. In our own solar system, the outer planets orbit the Sun more slowly than the inner ones, because the Sun's gravity weakens with distance. By that logic, stars at the edges of a galaxy should orbit more slowly than stars near the center, where most of the visible mass, the stars and glowing gas, is concentrated. But when astronomers like Vera Rubin carefully measured the rotation of spiral galaxies, they were astonished. The stars in the outskirts were moving just as fast, or even faster, than those closer in. It was as though some extra gravity was gripping those outer stars, preventing them from flying away into space. At first, this was a deep mystery. What could be providing that additional pull? The visible galaxy simply didn't have enough mass to hold on to those fast-moving stars. The same mystery appeared in galaxy after galaxy, and even in clusters of galaxies swarming together in the depths of space. In the 1930s, an astronomer studying a distant cluster noticed the galaxies were zipping around so quickly that by rights, the cluster should have torn itself apart. Clearly, some hidden mass, far more than what could be seen, was keeping everything bound together. Some wondered if gravity itself behaved differently on the largest scales, but gradually the evidence for a huge unseen mass became overwhelming. Over time, scientists came to realize that the lion's share of matter in the universe is actually this invisible kind. Estimates suggest that for every kilogram of ordinary matter, the stuff that makes up stars, planets, and people, there are about 5 or 6 kilograms of dark matter hiding in the shadows. In other words, the vast majority of matter in the cosmos is dark and unseen. It forms enormous halos around galaxies, extending well beyond the edge of the visible starlight. Every galaxy, including our Milky Way, is embedded in a huge sphere of dark matter, like a glowing firefly caught in an invisible glass ball, a halo of mass stretching far beyond the farthest stars of the galaxy. The stars and nebulae we see are merely the inner core of a much larger, hidden structure defined by dark matter's gravity. Because dark matter neither emits nor absorbs light, it took ingenious methods to confirm it was really there. One way was by using gravity as a kind of cosmic spotlight. Massive objects bend the path of light, an effect predicted by Einstein's theories. In some galaxy clusters, astronomers observed distant galaxies appearing distorted or oddly duplicated, as if seen through a curved lens. The amount of distortion revealed that the cluster's gravity was far stronger than what all the visible matter could account for. Ultimately, scientists concluded there must be a vast cloud of invisible mass in the cluster, bending light with its gravity exactly as dark matter would do. In one dramatic case, 2 galaxy clusters collided and passed through each other. As they did, the hot gas in each cluster slammed together and slowed down, but the galaxies and the dark matter barely interacted and sailed on past. Astronomers observed that in this collision, known as the bullet cluster, the sources of gravity and the visible gas separated from each other. The gas was left behind, glowing in X-rays, but the dominant gravitational pull moved ahead with the galaxies, a clear sign that most of the mass was in an invisible form that doesn't collide with gas or slow down. This became one of the most striking confirmations that dark matter is real and distinct from ordinary matter. We still don't know exactly what dark matter is made of. It could be composed of exotic particles, unlike anything we've yet detected in our laboratories. Scientists have given these hypothetical particles names like WIMPs or axions, and they have built elaborate experiments deep underground to try to catch a rare interaction between dark matter and normal matter. In those quiet, shadowy laboratories, great vats of ultra-cold liquid and sensitive sensors lie in wait for the tiniest spark or whisper of a dark matter particle colliding with an atom. So far, these particles have evaded capture, slipping through detectors just as effortlessly as they slip through the rest of the world. It's as if dark matter is a shadow cast by physics we have yet to fully understand. Yet, even without knowing its identity, we can trace dark matter's crucial role in cosmic history. In the early universe, long before the first stars ignited, dark matter was already hard at work. While photons of light kept ordinary matter buoyant and dispersed in a hot plasma, dark matter, unaffected by light, began quietly clumping together under its own gravity. It formed a kind of invisible scaffolding, gathering into dense concentrations, seeds for future galaxies. Later, when the universe cooled and ordinary matter could finally start to fall freely under gravity's influence, it fell into the regions where dark matter had piled up. The dark matter clusters acted like deep wells, pulling in gas that would form stars and galaxies. Without this head start provided by dark matter, the cosmos might have taken much longer to develop the rich structures that we see today. Even now, dark matter holds galaxies together in its soft gravitational embrace. It keeps stars bound in their galactic orbits and anchors clusters of galaxies so they don't drift apart. In a very real sense, dark matter is the glue of the cosmos, an invisible glue that binds the shining stars into grand configurations. Picture a vast, delicate spiderweb spanning the sky, with shimmering galaxies clinging to its filaments. The silk of that web is woven from dark matter. Wherever we find great collections of galaxies, we know that an even greater hidden mass is lurking there, choreographing their dance. The idea that such a dominant substance could be essentially invisible is both humbling and enchanting. It reminds us that reality can hide its most substantial ingredients in plain sight, eluding our direct perception. We gaze out into space with our best telescopes and see billions of galaxies. Yet we understand that what is visible is only a small portion of all that exists. The rest lies in quiet obscurity. Bit by bit, scientists are peeling back the layers of this mystery. With each observation of starlight bending or galaxies moving in peculiar ways, we get one step closer to glimpsing the full picture of this hidden mass. As we continue our journey, we leave behind the hidden matter that acts as the universe's foundation and turn to another deep mystery. If dark matter is the invisible scaffolding holding everything together, there is an equally strange phenomenon that pushes everything apart. Just as dark matter quietly pulls with its gravity, this other force, dark energy, works in the shadows to drive the universe's expansion faster and faster. In the next leg of our exploration, we will listen for the soft whisper of dark energy, the force that is accelerating the cosmos on the grandest scales. For a long time, everyone assumed that the expansion of the universe must be slowing down. After all, gravity is always pulling. The combined gravity of all the galaxies should be tugging at each other, gradually putting the brakes on the expansion that began with the Big Bang. It was a reasonable assumption, like expecting a thrown ball to eventually slow and fall back to the ground. But the cosmos had a surprise in store. In the late 20th century, astronomers began measuring the distances to far-off exploding stars, luminous supernovae that serve as cosmic mileposts. They wanted to see how the expansion of the universe has changed over time. To their astonishment, those distant supernovae were dimmer than expected, as if they were farther away than they should have been. The implication was stunning. Instead of decelerating, the expansion of the universe was actually accelerating. This discovery felt as if we had gently pressed the brakes on a car, only to find the car speeding up on its own. At first, many scientists found it hard to believe. It was so contrary to expectation. But soon additional evidence from other cosmic observations made it clear that an unseen influence was truly at work. The cause of this cosmic acceleration was completely unknown, so scientists gave it a placeholder name: dark energy. The term dark reflects our ignorance of its true nature, much as with dark matter. And energy hints that it might be a property of space itself, an energy woven into the very fabric of the cosmos. Dark energy seems to be everywhere, quietly pushing outward on space with a repulsive effect. It doesn't clump into galaxies or clusters like matter. Rather, it appears to uniformly fill the universe, like a subtle pressure that acts on the grandest scales. One way to imagine dark energy is to think of it as a kind of anti-gravity, or perhaps a persistent outward springiness built into space, as if the fabric of space-time itself has an innate urge to expand. It's incredibly feeble on small scales. You don't feel space pushing you apart in a room, and even within a galaxy, its effect is negligible compared to gravity. But over the vast distances between galaxies, dark energy's whisper becomes significant. Over billions of light years, this gentle outward force adds up, overcoming the pull of gravity. The result is that galaxies far away from each other feel an ever-increasing push to separate. Space itself is stretching at an accelerating pace, carrying galaxies along like corks on a fast-flowing river. We don't yet know what dark energy actually is. It might be an inherent property of empty space, what Einstein once referred to as the cosmological constant. In Einstein's time, the idea of a repulsive force in space was a curious mathematical fix, something he introduced to balance the universe and later dismissed as a mistake. But decades after Einstein, that very concept seemed to come alive in the data, a constant energy of the vacuum that makes space expand faster. Alternatively, dark energy could be something more exotic, a new field or fluid permeating the cosmos, perhaps one that changes subtly over time. For now, all we truly have is a name and measurements of its effects. It remains one of the deepest mysteries in science. What we do know is that dark energy dominates the universe today. Roughly 68% of the total energy in the cosmos is in this strange form. The rest, by comparison, includes about 27% dark matter and only 5% or so ordinary matter. All the atoms and light that we are familiar with. This means that the fate of the universe is largely governed by dark energy's behavior. Since its push is currently winning over gravity's pull, the expansion of the universe will likely continue to speed up. In the very distant future, galaxies that are not bound together may be flung so far apart that their light can no longer reach one another. Eons from now, an observer in our galaxy might see nothing but darkness beyond our local group of galaxies, because all other galaxies will have receded out of view. The night sky, now sprinkled with countless faint galaxies, would eventually become eerily empty of them. Where once there were delicate smudges of light from myriad galaxies, there would be only blackness beyond our own island of stars. It's a profound and somewhat melancholic thought, that the universe we see now, so rich with galaxies, is in a temporary phase. We live in a fortunate time in cosmic history, when distant galaxies can still be seen like lanterns in the dark. Far in the future, the universe will look emptier, but today we can witness its full splendor. We also take comfort in the fact that these changes unfold on timescales of many tens of billions, even trillions, of years. For the foreseeable future, our cosmic neighborhood will remain familiar. Dark energy's influence, though immense, is very gentle from moment to moment. Like a slow, inexorable tide across the cosmos, a gradual swelling that only becomes apparent when watched over eons of time. Scientists continue to study this subtle force, mapping how the expansion rate has changed throughout cosmic history. They look at distant supernovae, the distribution of galaxies, and the ancient light of the cosmic microwave background for clues about dark energy. Each piece of evidence is like listening for that quiet whisper in the dark. We've learned that roughly 5 billion years ago, dark energy's push overtook gravity's pull, and since then, the universe has been accelerating. We are essentially living in an age of dark energy, where its effect grows with every passing eon. Dark energy teaches us how dynamic and surprising the cosmos can be. Just a few decades ago, we didn't even suspect it existed. Now it appears to be the primary driver of the universe's evolution on large scales. It reminds us that the cosmos still holds secrets that can upend our understanding. In the same way that dark matter urged us to rethink what makes up the universe, dark energy urges us to rethink how the universe will grow old. Our journey through the universe's strange secrets has taken us from the beginning of time to the forces that shape its expansion. We have peered at invisible matter and pondered an unseen energy. Now, before we conclude this part of our voyage, let's step back and take in the grand design that all these elements shape together. Dark matter, dark energy, gravity, and quantum chance, working over billions of years, have woven a vast cosmic web, an immense structure that connects galaxies across the emptiness of space. In our final chapter of this part, we float above the universe to behold this cosmic web and marvel at the pattern of the cosmos on its largest scales. Imagine we could step back and observe the entire universe from a great height, watching over billions of galaxies at once. What would we see? We wouldn't find galaxies scattered randomly like grains of sand. Instead, we'd behold a vast pattern, an immense cosmic web stretching across the darkness. In this web, galaxies are not isolated. They are arranged along gossamer filaments and clustered at the intersections, like dew droplets clinging to the strands of a giant spider's web. Between these filaments lie enormous voids, vast regions of space where very few galaxies shine at all. The overall impression is of a delicate, lace-like structure on the grandest possible scale. This cosmic web is the large-scale structure of the universe. It formed over billions of years as gravity pulled matter into patterns dictated by those primordial seeds from the Big Bang. Long ago, when the universe was young and slightly lumpy with tiny variations in density, dark matter began to draw material into the denser regions. As time went on, these regions grew into lengthy filaments and massive clumps. Galaxies took shape within them, lighting up the densest threads and nodes of the web. The quieter voids in between grew emptier, as matter was gravitationally attracted toward the filaments, leaving vast expanses with only a sparse sprinkling of galaxies. Today, when we map the positions of tens of thousands of galaxies in space, we clearly see this web-like design, an interconnected network of galaxy clusters, lines, and almost cavernous voids. One of the striking things about the cosmic web is its scale. The filaments of galaxies can stretch for hundreds of millions of light-years from end to end. The voids can be similarly gigantic. Some span tens of millions of light-years across, containing hardly any galaxies at all. Some voids are so immense and empty that they contain only a few galaxies in a space that would normally hold thousands. One such region, sometimes called the Great Void, spans over 300 million light-years, with scarcely any galaxies inside, a true cosmic cavern of emptiness. Even the smaller tendrils between galaxy groups can be millions of light-years long. To give a sense of size, a single one of these cosmic filaments could easily encompass dozens of galaxy clusters and thousands of individual galaxies. Our own Milky Way, for instance, is part of a local filamentary structure, connected through our neighbouring galaxies to the Virgo cluster and other groups in our vicinity. All of this, in turn, is a segment of a much larger pattern that we call the Laniakea supercluster, an immense collection of galaxies and galaxy groups that our Milky Way calls home. Yet even Laniakea is just one concentration within the endless cosmic web. In the denser knots of the web, where filaments intersect, lie the great clusters of galaxies. These are regions where hundreds or even thousands of galaxies are bound together by gravity in a tight clump. They mark the hubs of the cosmic web, the cities in this galactic landscape. One famous example is the Coma Cluster, a cosmic metropolis of galaxies residing at a node of the web about 300 million light-years away. In that cluster, over 1,000 galaxies are swarming together. The pull of gravity there is intense, often heating gas to extreme temperatures, and even bending the light from background galaxies. Signs of the deep gravitational wells dominated by dark matter. Galaxies within clusters can collide or merge, and new stars are born amid the commotion. Over billions of years, these clusters have grown larger by drawing in material along the filaments, rather like rivers flowing into a sea. The filaments themselves are highways for matter. Galaxies move along them, drawn by gravity toward the clusters at filament intersections. Hot, diffuse gas also streams through these cosmic arteries, feeding galaxy formation along the way. Though the filaments are faint, composed mostly of dark matter and tenuous gas, astronomers have started to detect their presence directly. In recent years, with sensitive telescopes, scientists managed to capture a faint glow from hydrogen gas in a cosmic filament and observe how galaxies on opposite sides of a supposed void move relative to each other. These observations confirm what simulations had long predicted. Galaxies are aligned in long strings, and between them stretches the dim outline of dark matter's scaffolding. Using supercomputers, researchers can even recreate miniature universes in their labs. Starting from tiny density ripples, these simulations show filaments and clusters emerging naturally under gravity. The resulting pattern in a simulated cosmos looks strikingly like the real cosmic web we observe. That gives us confidence that our theoretical understanding of how these immense structures form is on the right track. Now, imagine yourself aboard a spacecraft, drifting along one of these filaments. You depart a crowded galaxy cluster, leaving behind the brilliant swarms of galaxies bound together in that hub. As you travel outward along the filament, galaxies grow sparser. You pass the occasional lone galaxy, strung out like a solitary streetlight, guiding your way through the vast night. Eventually, you find yourself in the middle of a great cosmic void. The galaxies behind you fade to tiny specks and then vanish. And ahead, there is mostly darkness, perhaps just the faint, distant glow of a far-off cluster, barely perceptible. The emptiness is immense and quiet. But if you continue onward, slowly, a few faint galaxies begin to appear again, growing more numerous as you approach the far side of the void. You realize you're entering another filament of the web. More galaxies line your path once again, and before long you arrive at a new cluster, a bustling city of galaxies lighting up the darkness. Traversing the universe in this way would be like crossing a spider's web, moving from knots of light through vast stretches of darkness to reach other knots of light. If we could see dark matter with our eyes, the cosmic web would likely appear even more pronounced. We would observe vast, ethereal tendrils weaving through space, with luminous galaxies just sparkling on their surfaces. It might look a bit like a three-dimensional foam, or the filaments of a gigantic neural network, a tracery of matter and light. Interestingly, scientists have noted that the large-scale structure of the universe bears an uncanny resemblance to other complex networks, such as the web-like patterns of neurons in a brain, or the distribution of matter in foamy bubbles. It seems that nature, at vastly different scales, loves to form intricate networks. Our perspective of the cosmic web has grown over time. Early galaxy surveys in the late 20th century first revealed hints of immense structures, gigantic walls of galaxies and yawning voids. One discovery was the Great Wall, an enormous chain of galaxies stretching over 500 million light-years. Since then, as we have mapped more of the sky in 3 dimensions, we've uncovered a rich tapestry of structure. We realized that what once looked like isolated superclusters are actually connected parts of this continuous web. It transformed our understanding of the cosmos. The universe is not a random sprinkle of galaxies, but a structured fabric with patterns that echo the initial ripples from the dawn of time. At the heart of this cosmic web lies the interplay of dark matter and gravity. Dark matter, invisible though it is, provides the scaffolding, the underlying framework on which this vast design is built. In the early universe, dark matter collected in filamentary shapes, and ordinary matter followed the dark matter's gravity, flowing into the same configurations. Thus, the glowing galaxies trace out where dark matter is densest. We live in the luminous embroidery on a hidden canvas. To picture it, imagine an elaborate invisible lattice stretching out in all directions. Here and there, where the lattice nodes are especially dense, galaxies light up like bright dew on a web. In between, where the lattice is sparse, there is darkness and void. The cosmic web is not static either. Over enormous spans of time, it evolves. Galaxies within filaments slowly migrate toward clusters, making the rich get richer. Clusters merge and grow, and voids expand as they are emptied of matter. The expansion of the universe, accelerated by dark energy, also plays a role, gradually pushing the strands of the web farther apart from one another. Billions of years in the future, the cosmic web may stretch even thinner, with each cluster becoming more isolated as the space between them widens. But the pattern itself, the local clustering of galaxies into filaments and nodes, will remain a feature of our universe for a very long time to come. Contemplating the cosmic web gives us a sense of perspective, unlike any other. We find that our galaxy, with its hundreds of billions of stars, is just one glittering node on a filament in a colossal network. Every galaxy is part of a larger structure, influenced by the gravity of its neighbors near and far. In fact, most of the cosmos by volume is comprised of those dark voids. The luminous galaxies and clusters occupy only a thread-like skeleton of all space. Even the emptiness of the voids is a product of those same cosmic relationships, as matter consolidates elsewhere. It underscores how interconnected everything is on the grandest scale. As we drift in our mind's eye above this vast web, there is a peacefulness in the view. The galaxies, like tiny points of light, outline the otherwise invisible architecture of existence. We see the grandeur of the cosmos's design, chaotic in detail perhaps, but ordered in its overall form. It's a silent and majestic symphony, billions of galaxies moving to the pull of gravity, arranged in filaments over unfathomable distances. Our journey through the universe's strangest secrets in this part has taken us from pondering what came before time to tiny quantum seeds that sparked galaxies, to the ghostly matter that holds those galaxies together, and the gentle force that is driving them apart, all culminating in the breathtaking vision of the cosmic web that connects them. This is the stage on which cosmic history unfolds. And yet, there are even more wonders and mysteries out there, waiting quietly beyond the horizon of what we've discussed. The cosmos is vast, and our exploration is far from over. For now, we let the curtain fall on this panorama of galaxies and dark threads, knowing that in chapters to come, we will continue to wander among the stars and delve into new cosmic mysteries, seeking the secrets that remain to be discovered. The story of the universe is far from complete. Now, our journey carries us into the realm of galaxies, where strange secrets lie hidden among the stars. Floating in the silent ocean of space, countless galaxies glow like distant lanterns in the dark. Yet not all galaxies announce themselves with brilliant light. Some are almost entirely hidden, so faint and diaphanous that they blend into the darkness, barely detectable. These are the ghost galaxies, nearly invisible realms of stars and dust that challenge our ability to even find them. One example of a ghostly galaxy is a colossal spiral known as Malin 1. Despite spanning roughly 650,000 light-years across, over 6 times the diameter of our Milky Way, Malin 1 remained undiscovered until 1986 because its stars are spread out so thinly. To our telescopes, this giant appears only as a dim smudge against the blackness. Its spiral arms are incredibly diffuse, containing stars and gas so sparse that the entire galaxy emits only a soft whisper of light. Astronomers have also found ghostly galaxies that are large in size, yet almost entirely dark. In the Coma cluster of galaxies, for instance, they identified an object called Dragonfly 44, a galaxy as massive as the Milky Way, but with hardly any visible stars. Measurements revealed that 99.99% of Dragonfly 44's mass is not in stars at all, but in unseen dark matter. Only a tiny fraction of this galaxy's material shines. The rest lurks invisibly, binding the galaxy together with its gravity. Discovering a Milky Way-sized galaxy, made of almost nothing but darkness, was a shock to astronomers. And Dragonfly 44 turned out not to be alone. Many such ultra-diffuse ghost galaxies have since been spotted hiding in distant clusters. Ghost galaxies come in smaller forms as well. Dozens of extremely faint miniature galaxies have been found lurking around our own Milky Way. These little systems contain only a few hundred or thousand stars, so few that they eluded detection until sensitive sky surveys revealed their presence. Astronomers were puzzled at how these dwarfs can be so star-starved. By using the Hubble Space Telescope to study a handful of them, researchers discovered that all the stars in these tiny galaxies are ancient. They all formed over 13 billion years ago, then star formation abruptly stopped. It seems that something in the early universe turned off these baby galaxies in unison. The leading explanation is cosmic rayonization, the era when the first generations of stars and quasars flooded the young universe with searing ultraviolet light. Those intense rays likely stripped the ghost dwarfs of their remaining gas and quenched their star-making, all around the same early epoch. In effect, the galaxies were too puny to shield themselves from this blinding cosmic sunrise. What little gas they had was boiled away as the ultraviolet flood swept through, like a candle flame extinguished by a sudden wind. Deprived of fuel, these tiny galaxies could no longer birth new stars, freezing them in a primordial, unfinished state. As a result, these faint dwarf galaxies are essentially fossils of the early universe, cosmic relics that haven't changed in billions of years. They still contain mostly old stars and are dominated by dark matter, the invisible mass that holds them together. Such ghostly dwarfs might also solve a long-standing cosmic riddle. Computer simulations predicted that the Milky Way should have had thousands of small satellite galaxies, yet only a few dozen have been observed. Where were the rest hiding? The discovery of ultra-faint ghost galaxies suggested an answer, Perhaps many small galaxies never formed much in the way of stars at all, rendering them almost invisible to us. There could even be countless more mini-galaxies that remain entirely dark, little clumps of matter where essentially no stars ever ignited. Such completely dark galaxies would be invisible in optical light, detectable only by their gravity or faint emissions. Many of these galaxies might yet remain undiscovered. Some ghost galaxies will remain forever faint and hidden, drifting quietly through the cosmos. Others may eventually meet a more dramatic fate. A tiny, star-starved galaxy can be pulled into a larger galaxy's gravitational embrace and torn apart, its few stars strewn like breadcrumbs into the larger system. In the cosmic ecosystem, even these shy ghosts can become prey. To explore that violent side of galactic life, we turn now to the cannibals of the cosmos. These are galaxies that feed on other galaxies. The Andromeda Galaxy, our nearest large galactic neighbour, appears as a tranquil mist of light in the night sky. But appearances can deceive. Andromeda is actually a cosmic cannibal. It has spent the eons consuming smaller galaxies, and the evidence still lingers in its halo. Astronomers have detected faint trails of stars arcing around Andromeda, the remains of dwarf galaxies that were torn apart and absorbed. These ghostly tidal streams are like cosmic scars, marking where a smaller galaxy's stars were ripped away by Andromeda's gravity. Galaxies that devour their companions leave behind telltale clues. When a wimpy galaxy ventures too close to a behemoth like the Milky Way or Andromeda, the smaller one is slowly pulled apart, its stars stretched out across space and integrated into the larger system. The liberated stars often trace enormous loops and streams wrapping around the predator galaxy. Over time, these stellar streams disperse, but for a while they remain as shimmering arcs, showing the path the doomed galaxy took before it was digested. Sometimes the aftermath of galactic cannibalism takes on an even more intricate pattern. As the stars from a devoured galaxy spread through the host, they can form shells and ripples, layered structures that bloom around the victorious galaxy's core. One striking example is the giant elliptical galaxy NGC 474. Hubble images reveal that NGC 474 is surrounded by several faint, concentric shells of stars. Astronomers think NGC 474 formed those shells by swallowing one or more smaller galaxies, sending a ripple through NGC 474's stars, like a pebble in a pond. In fact, roughly 10% of elliptical galaxies display such shell patterns, suggesting a past filled with mergers. In crowded galaxy clusters, cannibalism is even more rampant. At the centers of these clusters sit monstrous elliptical galaxies that have grown by consuming countless smaller galaxies over their lifetimes. They possess enormous, diffuse halos and often exhibit multiple tidal tails and shells. These are signposts of repeated feasts. A prime example is the giant elliptical in the Virgo cluster, known as M87, which has a sprawling envelope of stars believed to be the amalgam of many smaller galaxies eaten over billions of years. To such leviathans, the infall of each dwarf galaxy is just another snack, gradually adding to the giant's girth. For scientists, galactic cannibalism is a chance to watch cosmic evolution in action. The debris left behind, those tidal streams and plumes of stars, allows astronomers to piece together a galaxy's mealtime history. By mapping these streams, researchers can estimate how massive the larger galaxy is and how its mass, including dark matter, is distributed, because the shape of the tidal debris is influenced by the gravitational field. In this way, The corpse of a devoured galaxy tells the tale of its predator. Every elongated stream and arc of stars circling a galaxy is a testament to an act of cosmic consumption, helping astronomers understand how galaxies grow by merging with others. Not all galactic encounters are destructive in appearance, however. Some cosmic collisions produce mesmerizing shapes, vast rings and subtle ripples that spread through galaxies like patterns on water. Having explored the violent side of galaxy mergers, we next delve into these gentler-looking marvels, the rings and ripples that can emerge from galactic encounters. They reveal a creative side to cosmic collisions. One of the most arresting galactic shapes ever seen is a perfect ring of stars. The Cartwheel Galaxy is a spectacular example. It looks like a cosmic wheel suspended in space. A bright hub of older stars sits at the center, surrounded by an empty-looking gap, and then an outer ring studded with brilliant blue stars. It is a cosmic arrangement that defies the usual galactic forms. How could such a configuration arise? Astronomers believe the Cartwheel's unusual shape was born of a violent event. A smaller galaxy hurtled straight through the heart of a larger galaxy, right down the middle. This head-on collision sent a powerful shockwave coursing outward through the larger galaxy's disk, much like the ripples from a stone tossed into water. As that wave ploughed through gas and dust, it triggered an expanding ring of star formation. New stars ignited along the wave's leading edge, creating the glittering outer ring that we see today. The Cartwheel Galaxy, with its eerie symmetry, is essentially a cosmic ripple frozen in time, the aftermath of a bullseye collision still spreading out after 400 million years. Ring galaxies like the Cartwheel are rare, but they dramatically illustrate how cosmic accidents can produce order. When conditions are just right, typically one galaxy plunging through the center of another, nature draws a circle of stars. Some ring galaxies even have multiple rings or additional structures. The Cartwheel, for instance, has a smaller inner ring and faint spokes connecting to its outer ring, hinting at the complex dynamics stirred up by the collision. There are also peculiar systems like Hoag's object, a near-perfect ring of young stars, with a sphere of older stars isolated in its center. Hoag's object has no evident intruder galaxy nearby, making its origin something of a mystery. Perhaps a past collision or an unusual instability created its pristine ring. These cosmic rings remain one of the prettiest puzzles in the sky, each one a celestial laboratory for studying gravitational waves and star formation. Hoag's ring remains one of the universe's most photogenic anomalies. Not all galactic rings are as obvious as the Cartwheel's. Sometimes a galaxy retains a more subtle ripple or wave after an interaction. Even our Milky Way shows signs of such perturbations. Astronomers mapping the positions and motions of stars in the Milky Way's outer disk have found odd ripples and oscillations. The cause appears to be an ongoing collision with the Sagittarius dwarf galaxy, which has dived through the Milky Way's plane multiple times. Like a boat creating waves as it passes through water, the Sagittarius dwarf's passages set our galaxy's disk of stars to wobbling up and down. These wave-like disturbances propagate through the Milky Way's vast disk, and although they are faint, they have been detected in precise stellar surveys. It is humbling to realize that our own galaxy is still ringing from a recent encounter, a silent reverberation of a dwarf galaxy's plunge, echoing across tens of thousands of light years. Our galaxy, in a sense, still bears the subtle scars of that encounter. In time, the Milky Way's disk may settle, but for now, it gently vibrates with the memory of that cosmic meeting. While rings and ripples tell us about galaxies' external dramas, an even stranger secret lies tucked deep in the core of galaxies. To uncover it, we must venture into the heart of darkness, into the central regions where supermassive black holes reside. These black hole cores are the invisible engines that can outshine entire galaxies and shape their fates. They are truly the beating hearts of active galaxies. Deep in the center of a galaxy, beyond all the shining stars, there is an abyss. Astronomers have learned that a supermassive black hole lies at the heart of nearly every large galaxy. This dark object is like a hidden engine in the galactic core, often quiet but capable of tremendous power. When a black hole feeds on gas or stars that wander too close, it can erupt in a blaze of energy, turning into what we call an active galactic nucleus. In fact, the brightest objects we see in the distant universe, quasars, are actually the brilliant cores of young galaxies, fueled by supermassive black holes devouring matter. These active galactic nuclei can outshine all the stars in their host galaxy combined, lighting up the cosmos from billions of light years away. It took decades for scientists to accept that such mighty black holes were real. Quasars were first noticed in the 1960s as star-like points with bewildering brightness and huge redshifts, and their true nature was uncertain. Gradually, evidence mounted that only a supermassive black hole could explain the energies involved. By the 1980s, many astronomers suspected supermassive black holes were the explanation, but direct proof was still lacking. A breakthrough came in the 1990s when the Hubble Space Telescope turned its gaze toward the center of the elliptical galaxy M87. Hubble observed a disk of hot, ionized gas swirling around M87's core at astonishing speed, about 1.2 million miles per hour. The motion of this gas revealed the presence of a monstrous black hole weighing billions of times the Sun's mass at the center of M87. Even more spectacularly, astronomers saw a narrow jet of plasma shooting out from M87's core, powered by the spinning black hole's magnetic grasp on infalling gas. This was direct proof. A supermassive black hole was not only there, but actively shaping its surroundings. We now know that supermassive black holes and galaxies evolve hand in hand. There is a remarkable link between a galaxy's central black hole and the galaxy itself. The bigger the galaxy's central bulge of stars, the more massive the black hole it hosts. This correlation hints that as galaxies grew over time, their black holes grew in tandem. When a black hole gorges on material, it doesn't simply hide its feast. It can influence the entire galaxy. As gas falls toward the center and heats up, the black hole's accretion disk and jets pour out energy. This outpouring can push away the remaining gas or heat it so much that it can't form stars. In essence, a feeding black hole can blow the whistle on starbirth in its host galaxy. Observations have confirmed this effect. For example, the Webb Space Telescope recently found a galaxy in the early universe where the central black hole is driving out huge amounts of cold gas, effectively starving the galaxy of the fuel needed to form new stars. Scenarios like this show how the black hole acts as a cosmic regulator. It can at times nurture star formation by stirring gas, but it often puts the brakes on a galaxy's growth by keeping fresh gas out. Even in galaxies where the central black hole is quiet, its presence is felt. Our own Milky Way's supermassive black hole, Sagittarius A, is relatively dormant today, detectable mainly through the motions of nearby stars. But evidence suggests it was more active in the geological past. Two enormous gamma-ray bubbles above and below the Milky Way's center, the Fermi bubbles, are thought to be the afterglow of a flare from Sagittarius A few million years ago. In those ancient times, our galaxy's core likely blazed with a faint accretion glow. Now, however, Sagittarius A slumbers, a sleeping giant. Someday, in the far future, if new material drifts into the galactic center, our black hole could awaken again, joining the ranks of active galactic nuclei for a time. From the nearly invisible ghost galaxies at the edge of detection to the brilliant fireworks of galactic cores, we have seen how much wonder and mystery is packed into these island universes. Yet our journey is not over. Beyond the scale of individual galaxies and their black hole hearts, even larger and deeper cosmic secrets await. In the next part of our exploration, we will venture outward and onward, probing the grandest and most enigmatic structures of the cosmos, continuing our quest to unveil the universe's strangest secrets. In the silent darkness of space, two stars can become locked in a fatal dance. They circle one another closely, bound by gravity, drawn ever nearer by their mutual orbit. One star is older and larger, swollen in size, its outer layers drifting unsteadily under weak gravity. The other star is smaller but fierce, and as they draw close, a stream of gas begins to flow. Gently at first, the smaller star pulls the tenuous outer atmosphere of its companion toward itself. Soon, a ribbon of starlight stretches between them, a glowing bridge of stolen matter. This is the realm of the vampire star, a celestial thief that feeds on its partner's life. As the hungry star siphons gas, it grows hotter and more luminous. It is rejuvenated by the fresh hydrogen fuel, burning bright and blue-white, as though it has drunk a potion of youth. Meanwhile, the victim star is left drained. Its once plentiful outer layers are stripped away, revealing a hot, barren core that flickers weakly. In time, the donor star may shrink and dim, a withered remnant of its former glory, all because its companion has cannibalized it. Astronomers long wondered at peculiar stars that did not fit their surroundings. In ancient star clusters, most stars are old, reddish, and fading. Yet hidden among them, there are occasional interlopers, bright, blue stars shining as if they were much younger. These odd, blue stragglers seem to be out of place and time, stars that by rights should have grown old and red like their neighbours, but instead glow with youthful vigour. For years, their existence was a mystery, a secret of the cosmos that defied the normal aging process of stars. The secret was eventually uncovered. These blue straggler stars are vampires. Each one has gained a new lease on life by consuming another star. Some likely merged outright, two older, smaller stars colliding and blending into one larger star that burns anew. Others are stealthier, slowly accreting gas from a close companion over millions of years. By stealing mass, the vampire star becomes more massive and hotter than it was ever meant to be at its age. It effectively resets its stellar clock, appearing younger than it truly is. The cluster around it continues to age and cool, but the vampire star blazes on, a renegade that has cheated aging through cosmic blood transfusions of hydrogen. Even outside of clusters, individual binary stars practice this celestial thievery. One famous example gleams ominously in the night sky of Earth, the star Algol in the constellation Perseus. To the naked eye, Algol mysteriously dims and brightens over a period of days, an eerie blinking that earned it the nickname the Demon Star in antiquity. For centuries, people found Algol's changes unsettling steeped in myth and superstition. Today, we know Algol is not a single star at all, but a binary pair engaged in a dramatic exchange. The larger star in the pair has had much of its atmosphere siphoned away by the smaller, hotter star. As they orbit, the donor star sometimes passes in front of the brighter companion, causing Algol's visible light to dip as if winking. Meanwhile, the transfer of mass continues unseen, a slow flow of gas spiraling onto the hotter star. Algol's peculiar behavior, its paradox of a smaller star shining brighter than a larger one, is explained by this act of stellar vampirism. This mass stealing can have profound effects on both stars' destinies. The vampire star swells with stolen fuel, living longer and sometimes becoming variable in brightness as it adjusts to its new mass. The victim star, having lost its outer layers, may be prematurely aged. It can contract and heat up, looking like a much smaller, hotter star than it started. Essentially, a stripped stellar core shining in exposed vulnerability. In some cases, the erstwhile victim might become a white dwarf, or another compact remnant sooner than it would have, hastened to its end by the vampiric encounter. Such interactions are not gentle affairs. As gas pours from one star to the other, it can form a swirling accretion disk around the vampire star, heating up to extreme temperatures and glowing in ultraviolet or X-rays. The process can produce flashes of energy, sudden bursts when the flow of gas becomes unstable. If the vampire star is a dense core like a white dwarf, the stolen matter can ignite in explosive flashes on its surface, creating nova outbursts that momentarily increase the system's brightness tenfold or more. These are like belches of a star that has overfed, ejecting some stolen gas in a sudden flare of light. Yet the star survives, and the feeding can resume again after the outburst. Knowing this, one might imagine that vampire stars are rare, lurking as exotic monsters in the cosmic darkness. But modern observations suggest the opposite. They are remarkably common, especially among close binaries. Many stars live in binary systems, and it turns out a substantial fraction of massive stars will interact with their companions during their lifetimes. Studies show that more than half of all massive stars engage in some form of mass transfer or merger. In effect, stellar vampirism is a normal chapter in the lives of many binary stars, rather than an isolated curiosity. The universe is full of these parasitic relationships, silently altering the life courses of stars. Picture a massive star and its slightly smaller partner locked in close orbit. Over millions of years, the more massive star evolves faster and expands into a red giant. Soon its outer layers overflow its gravitational hold, spilling toward the companion. The smaller star eagerly devours this material, gaining mass and spinning faster under the influx. The giant star, relieved of its envelope, may collapse into a small hot core, perhaps even contracting into a white dwarf if enough mass is lost, essentially ending its life early. Meanwhile, the companion star now shines as a blue-white star, far more massive and longer-lived than it originally was. The roles have reversed. The star that was born less massive ends up being the more massive survivor, and the originally massive star dwindles into obscurity. The two continue their dance, but both have been transformed by the encounter. For the vampire star, the stolen life can make it appear as though it cheated death. Instead of dying out when it should have, it burns on brightly, possibly for millions or billions of years longer than if it had remained alone. It carries in its core the mixed history of two stars, the fresh hydrogen from its victim allowing new fusion and extending its youth. If such a star resides in a cluster, it stands out like a youthful stranger at a reunion of elders. Its blue glow and high energy contrast sharply with the mellow red of its aging peers, telling a story of secret rejuvenation. From a distance, none of this drama is visible to the casual observer. Only careful measurements of star colors, brightness variations, and spectra reveal the tale. Astronomers detecting odd chemical signatures in some stars, like excesses of elements produced only in old, giant stars, realized those stars might have absorbed material from an evolved companion. For instance, a star enriched with rare heavy elements such as barium can be a sign that it stole matter from a companion that had produced those elements in its now lost giant phase. These clues are like fingerprints left after a stellar feast, evidence that mass transfer occurred. One by one, the mysterious cases of stars that shouldn't be so hot or so young were explained by these hidden acts of cannibalism. The blue stragglers in clusters, once perplexing, are now understood as the children of stellar mergers or mass theft. Algol's unsettling blink is now known as an eclipse in a binary star where vampirism has taken place. The concept of single-star evolution had to give way to a more complex picture. Stars, like living creatures, can interact, feed on each other, and alter each other's fates. In the grand cosmos, this is a quiet, ongoing theft, a slow siphoning that can last millennia or longer. There's no violence visible from far away, just the subtle brightening of one star and the gradual fading of another. If we could watch a time-lapse of a vampire star system over eons, we would see one star growing more radiant, spinning faster, while its companion swells, then shrinks, and turns ghostly. It's a hauntingly beautiful image. Two entwined stars exchanging matter, one essentially drinking in the essence of the other. Ultimately, the victim star may lose so much that only its core remains, and it transitions into the next phase of its existence prematurely. The vampire star, bloated with new fuel, might live on to eventually become something it otherwise could not. Perhaps even going supernova one day, thanks to the additional mass it gained. In a sense, the donor star sacrifices its future so that the other might have a different fate. It is a dramatic example of how the life of one star can profoundly influence another's destiny. Stellar vampirism adds richness to the tapestry of stellar life cycles. It shows that the lives of stars are not always solitary, predictable journeys from birth to death. Instead, stars can profoundly affect each other, exchanging material and energy in ways that make the universe's story more complex and intriguing. As we drift away from this scene of celestial theft, we carry the image of a shining star and its dim companion, forever linked by a bridge of stolen light. Theirs is a tale of survival and sacrifice played out in slow motion against the backdrop of eternity. From the quiet drama of binary stars secretly sharing life, our journey through the cosmos continues. We leave behind the vampire stars and their clandestine exchanges. Ahead lie stars with a different kind of strange behavior, not stealing light from a neighbor, but pulsing with their own mysterious inner rhythms. It is time to witness these cosmic heartbeat stars, gently throbbing in the darkness. High above the galactic plane, a lone star lives out a unique rhythm. Over the span of weeks, it gradually swells in size, its outer layers stretching outward and cooling. Its light grows softer and dimmer as it expands. Then, as if drawing a deep breath, the star contracts again, heating up and growing more luminous. This cycle repeats over and over, a steady throbbing in the cosmos. To a distant observer, the star's brightness rises and falls like the beat of a heart. Such a star is a variable star, one whose light is not constant, but modulates in a discernible pattern. It is as though the star were alive, inhaling and exhaling starlight in a cosmic, centuries-long meditation. In the 17th century, early sky watchers were astonished to find that one of the fixed stars was not fixed at all. A star in the constellation Cetus, the whale, would appear and disappear over the course of months. To the naked eye, it was there at one time, shining as a moderately bright star, and then later it was gone, invisible in the night sky, only to return again. This star was eventually named Mira, meaning wonderful or miraculous, for its seemingly magical vanishing act. Mira's cycle lasts about 11 months, during which it brightens to be visible without a telescope, then fades to near nothingness. In truth, Mira is not dying and reviving, but pulsating. It is a red giant star late in its life, and it expands and contracts in a slow, rhythmic pattern. When Mira swells to its largest size, its surface cools and emits less visible light, rendering it faint. When it contracts, it heats up and glows more brightly again. To ancient observers, this was nothing short of a cosmic mystery, a star that refused to hold steady like all the others. As telescopes improved and more observers kept watch on the stars, many other variable stars were discovered. Some varied slowly like Mira, others changed on faster timescales of days. In 1784, an English astronomer noticed that the star Delta Cephei periodically rose and fell in brightness over about 5 days. This star became the prototype of an important class of pulsating star known as Cepheid variables. Cepheids are giants or supergiants that pulsate in a remarkably regular way. Each Cepheid star has a stable period. It might pulsate every few days or weeks, and with each cycle, its brightness follows a distinctive pattern, brightening swiftly and dimming more slowly in each period. The pattern repeats with clock-like precision. It is as if these stars have an internal metronome, keeping perfect time in their oscillations. The mechanism behind this pulsation is hidden deep within the star's layers. As the star contracts under gravity, its interior heats up and pressure builds, causing the star to push outward again. In certain stars, there is a kind of valve effect, a layer of ionized gas that traps and releases energy periodically. When the star is compact, this layer absorbs heat and energy, eventually causing the star's envelope to expand. Upon expansion, the layer cools and becomes transparent, letting energy escape, and the star begins to contract once more. This cyclical storing and releasing of energy drives the entire star to oscillate in size and brightness. The result is a steady pulse that we can observe from afar as a rhythmic change in light. To the eye, a Cepheid's changes can be subtle, but with careful measurement, the star's light curve, a graph of brightness over time, is a beautiful, regular wave. These stars have another secret. Their pulsation period is directly linked to their true luminosity. In the early 20th century, astronomer Henrietta Swan Leavitt discovered that brighter Cepheids take longer to complete one cycle than dimmer ones. This period luminosity relationship turned Cepheids into one of the most valuable tools in astronomy. By measuring the period of a Cepheid's pulse, one can infer its actual brightness, and by comparing that to how it appears from Earth, determine its distance. Thus, these strange pulsing stars became cosmic lighthouses, guiding us to the true scale of the universe. Astronomers used them to gauge the distances to faraway galaxies, expanding our understanding of the cosmos. What was once a mysterious stellar quirk, a star's habit of blinking, became the key to measuring the heavens. Beyond the Cepheids, there are many other types of variable stars with their own rhythms. Some, like the RR Lyrae stars, are smaller pulsators that flash on timescales of hours. They too have their own steady beats and serve as beacons in old star clusters, telling us their distance and age. Others, like long-period variables including Mira, are red giants in their twilight years, pulsating slowly and often irregularly. These giants can have somewhat erratic cycles, with each peak of brightness not exactly the same as the last, hinting at the tumultuous changes in their vast, distended atmospheres. While many variable stars pulse in a single steady period, nature has created some with far more complex songs. A star can pulsate in multiple modes at once, like multiple notes playing simultaneously. When these pulsation modes overlap, the brightness variations can become intricate, sometimes nearly chaotic. In recent times, astronomers studying data from space telescopes like Kepler have uncovered stars exhibiting surprisingly complex rhythms. One star, for instance, was found to have two pulsation frequencies that were in an irrational ratio, roughly the golden ratio, 1.618 to 1. This meant the star's light never repeated the same pattern exactly, yet it wasn't random either. The two rhythms interfered to create a mesmerizing quasi-pattern, a cosmic harmony of two notes that never align into a simple repeat. Such behavior was wholly unexpected, a mathematical curiosity shining in the sky. To some, the irregular yet patterned pulsing of that star looked almost like a signal, a coded beacon. In fact, speculation briefly ran wild that perhaps an alien civilization was modulating the star. But further analysis revealed it to be a natural phenomenon. The star was oscillating in a state between order and chaos, a testament to the rich complexity of stellar physics. Even in its natural origin, this golden ratio pulsation felt like a message in numbers, written in starlight across space. These pulsating stars serve as more than just distance markers or mathematical marvels. They are windows into the hearts of stars. Each oscillation is essentially a sound wave echoing through the star's interior, albeit at frequencies far too low for any human ear, the star's own music. By studying these vibrations, scientists can infer what the inside of a star is like, similar to how one might deduce the structure of a bell by listening to its tone. The science of astroseismology treats these brightness changes as seismic waves, revealing the density and composition of stellar cores and layers. It is remarkable that by simply observing a star's flicker, we can peel back its outer layers in our understanding and glimpse the processes deep within. For a lay observer, though, beyond all the science, there is an intrinsic wonder to a star that pulses. Imagine gazing up at the night and noticing a star that subtly, steadily changes, almost as if alive. These stars remind us that the sky is not static at all. It has its rhythms and breaths. Their light curves are like celestial heartbeats, steady or irregular, but each unique. In some sense, they bring a hint of gentle unpredictability to the night sky, a reminder that even in the vast silence of space, there is rhythm and music. Even our own sun has its pulsations, though on a much smaller scale. The sun quivers with millions of tiny oscillation modes that cause it to ring like a faint bell. We cannot see this by eye, but instruments detect these subtle motions as the sun's surface ripples. These are the sun's internal pressure waves bouncing around inside it. Most stars likely pulsate to some degree as they age or as conditions in their cores change. But only certain stars pulsate enough to noticeably change their brightness to our eyes or telescopes. The variety of variable stars is staggering. Some pulsate with clockwork regularity. Others vary irregularly because they pulsate in multiple modes at once, or because they undergo cycles of upheaval. And not all variability is due to pulsation. Some stars dim because something passes in front of them, like eclipsing binaries, or because of giant star spots on their surfaces. But the pulsating stars stand out for the way the star itself is changing intrinsically, breathing in and out. They show us that a star is not a simple, unchanging orb, but a dynamic sphere of plasma that can oscillate and resonate like a musical instrument. Under the telescopic eye, the North Star, Polaris, long appeared nearly constant in brightness. Only in the last century did astronomers discover that Polaris is actually a Cepheid variable, albeit a very subtle one. It pulsates gently, a sign that even the pole star is not immune to the cosmic beat. Some Cepheids can even change their pulsation rates over decades as their structure slowly evolves, a reminder that nothing in the cosmos stays the same forever. As we drift from one pulsing star to another in our thoughts, we experience the cosmic dance of light and time. There is a peaceful reassurance in the steadiness of a Cepheid's rhythm, like a lighthouse flashing reliably across dark waters. And there is a captivating mystery in the more erratic flicker of a star, like Mira, slowly changing as it sheds its outer layers. These stars quietly insist that the universe has its rhythms, some steady, some complex, all beautiful. In the darkness between pulses, as a star momentarily dims, there is a sense of suspense, and then it brightens again, fulfilling the promise of its cycle. These strange rhythms have guided explorers of the cosmos and challenged our imaginations. We leave these beating stellar hearts with a sense of admiration. They have taught us that even in the vacuum of space, there is a kind of heartbeat, a gentle cosmic pulse. Stars that pulse remind us of the vibrancy hidden in the cosmos's seeming stillness. But not all stars end their story with such lively oscillations. Eventually, many pulsating stars, and indeed most ordinary stars, will settle into a final quiet state. In the next stage of our journey, we will encounter the remnants of stars that have exhausted their fuel, the faint, enduring embers known as white dwarfs, which cool and fade for eons in the dark, like immortal stars waiting out the end of time. Drifting through the hushed cosmic graveyards, we find faint stellar embers glowing in the dark. These are white dwarfs, the cores of once mighty stars, now stripped of their outer shells and left to cool for eternity. A white dwarf may shine with a bluish-white hue when it's freshly made, its surface still incredibly hot from the star's recent death throes. But it is a silent light, generated not by ongoing fusion, but by stored thermal energy, slowly radiating away. With no new fuel to burn, the white dwarf will gradually fade, its glow diminishing over billions upon billions of years. In the cold vacuum of space, it will persist, an almost eternal cinder, slowly losing warmth, but never truly extinguished within any time frame we can fathom. Every white dwarf has a history. Long ago, it was the heart of a star like our Sun, or perhaps an even larger star. When such a star reached the end of its life, it swelled into a red giant and cast off its outer layers. For a brief time, those cast-off layers formed a glowing planetary nebula, a beautiful halo of gas expanding into space. At the center of that nebula remained the core, exposed, compressed, and fiercely hot. That naked core is the white dwarf. Typically about the size of Earth, yet containing mass comparable to the Sun's, it is an object of extreme physics. In its heyday, this core was where the star fused helium into carbon and oxygen. Now that fusion has ceased, the core has no outward pressure from nuclear burning. Gravity has squeezed it to a density beyond imagination, and only the quantum degeneracy pressure of electrons, a quantum mechanical resistance to further compression, holds the star up against collapse. The result is an ultra-dense, compact star that will not shrink further, but simply sit in the darkness and cool. When astronomers first encountered a white dwarf, it defied their expectations. The brightest star in Earth's night sky, Sirius, was found to have a tiny, faint companion orbiting it. Sirius B, a white dwarf. Through telescopes, Sirius B was dim, yet blue-white, indicating it was extremely hot. Calculations showed it had a mass nearly equal to the Sun's, yet it was no larger than Earth. This was astonishing. How could so much matter be packed into such a small volume? The idea was almost unbelievable. A new kind of star, unlike the airy, blazing giants we knew. One astronomer remarked that a teaspoon of Sirius B's material would weigh tons. Indeed, on Earth, a teaspoon of white dwarf matter would weigh on the order of 5 tons, about as much as an elephant, because its substance is packed so tightly. This discovery was our first glimpse into the exotic end state of stellar evolution. White dwarfs glow with a hard, white light when young. Some have surface temperatures exceeding 20,000 degrees Celsius just after formation. But without an energy source, they begin a long cooling process. After millions of years, they may cool to a yellow-white, then to red as the millennia pass. Imagine an iron poker pulled from a fire. At first it's white-hot, then it becomes red-hot, and eventually it fades to a dim cherry glow, and finally to black. So too does a white dwarf fade, only on a vastly longer timescale. The oldest known white dwarfs have cooled for nearly the age of the universe, and now shine feebly with reddish or orange hues, only a tiny fraction as bright as they once were. Yet they still emit some light and heat, testifying to their residual warmth even after 13 billion years. In time frames beyond human comprehension, these stars will continue to radiate and cool. Trillions of years from now, long after our sun and neighboring stars have vanished or evolved, the white dwarfs will still be there, ever weaker, approaching a final darkness. Eventually, in theory, a white dwarf will become a black dwarf, emitting no visible light, just a cold mass in the abyss. But our universe is not old enough for any black dwarfs to exist yet. Even the oldest white dwarfs are still warm enough to glow faintly. In this sense, white dwarfs are practically immortal on cosmological timescales. They will be the last stars shining after all others have burned out. And even then, they will only slowly wink out, one by one, perhaps quadrillions of years in the future. It is a strange kind of immortality, not the active life of a shining sun, but a slow fading that stretches across eternity. Despite their quiet appearance, white dwarfs are fascinating in their own right. Their surfaces can be extraordinarily pure, usually composed of hydrogen or helium. The immense gravity of a white dwarf, hundreds of thousands of times stronger than Earth's, pulls heavier elements down into the interior, leaving only the lightest elements to float on top. This means we often see only a thin veil of hydrogen or helium when we observe a white dwarf's spectrum, even though its core is made of carbon and oxygen. In some cases, as the star cools, the carbon and oxygen may crystallize, forming something akin to a giant diamond in space. In fact, astronomers have evidence that very old, massive white dwarfs undergo a phase transition where their interior solidifies into crystal. One famous example is a white dwarf about 50 light-years away that has partially crystallized. It's sometimes whimsically referred to as a cosmic diamond. Such poetic imagery is fitting. After all, diamonds on Earth are formed under high pressure, and in a white dwarf, nature takes that to an extreme cosmic scale. Occasionally, white dwarfs can still surprise us with a last flicker of activity. If a white dwarf is in a close binary and siphons matter from a companion, a process akin to the vampirism we discussed earlier, it can undergo nova outbursts, surface explosions that cause it to brighten temporarily. However, these events don't destroy the white dwarf. They are more like hiccups. The white dwarf returns to its cooling state afterward. In rare cases, if enough mass is accumulated, a white dwarf can be pushed over a critical mass limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. If that happens, the white dwarf detonates in a thermonuclear supernova, obliterating itself entirely in a brilliant flash. But absent these interactions, an isolated white dwarf is a model of stellar serenity, quietly shining and diminishing, essentially forever. The night sky contains many white dwarfs, but most are too faint to see without telescopes. They hide in plain sight, as the remnant cores of planetary nebulae, or as companions to more luminous stars. If you look at the constellation Lyra, for instance, the famous Ring Nebula is the ghostly shroud of an old star, and at its center lies a tiny white dwarf that once was that star's heart. Through a telescope, you can discern the little point of light in the nebula's center, a beacon of what remains after a star's outer beauty has drifted away. There is something profoundly peaceful about a white dwarf. After the tumultuous phases of stellar evolution, the red giant's expansion, the throes of ejected layers, the white dwarf is a final simplicity. No more nuclear burning, no more dramatic changes in size or luminosity, save the steady decline. It just exists, a hot sphere of degenerate matter cooling imperceptibly slowly. If we could stand on a hypothetical planet orbiting a white dwarf, though such a planet would be cold and dimly lit, the white dwarf might look like a small, intense pinprick of light in the sky, illuminating its surroundings with a stark, steady glow. Over many generations, inhabitants might notice their sun dimming ever so slightly, the daylight fading from one epoch to the next, a gentle, inevitable dwindling of warmth and light. White dwarfs also contain matter in an exotic state. The densities crush atoms into a form where electrons roam freely and nuclei are packed closely, an environment wildly different from normal stars. One could say a white dwarf is a star made of atom ashes, the remaining nuclei of what once was a shining star, now packed shoulder to shoulder in a cosmic cinder. This too contributes to their longevity. Without fusion or much movement possible in the tightly packed interior, not much happens aside from gradual cooling. In the far future of the universe, when new star formation has ceased and the big galaxies have dimmed, the white dwarfs will represent the last flickers of light, like red-hot coals in a vast cold fireplace. They'll glow until their last heat is spent. It is a melancholic, yet strangely comforting image. Even as cosmic night eventually falls, it will not be completely dark for a very, very long time. thanks to these tiny, steadfast embers. Having spent time in the calm presence of white dwarfs, we now prepare to encounter a very different kind of stellar remnant. Where white dwarfs are serene and enduring, the remnants of more massive stars can be turbulent and violent. If a star many times the mass of the Sun collapses, it doesn't become a gentle white dwarf. It crushes itself into a neutron star, an even denser object. And on rare occasions, those neutron stars possess magnetic fields so intense and volatile that they challenge our understanding of physics. Our journey moves from the quiet immortality of white dwarfs to the furious energy of magnetars, the most magnetic objects in the universe, where the calm of space is shattered by bursts of unimaginable power. In a remote corner of our galaxy, a sudden flash of high-energy light erupts without warning. For a brief moment, it outshines all the stars in the Milky Way, a crackling blaze of gamma rays and X-rays racing across space. This is the fury of a magnetar, one of the most fearsome objects known. Magnetars are neutron stars, the collapsed cores of massive stars that died in supernova explosions. But they are no ordinary neutron stars. They possess magnetic fields of staggering intensity, the strongest magnetic fields in the cosmos. To grasp how extreme, consider that Earth's magnetic field, which gently guides compass needles, is about a single unit on the scale of Gauss. A typical fridge magnet is a few hundred Gauss. A normal neutron star's field might be a trillion Gauss. But a magnetar's field can reach 100 or even 1,000 trillion Gauss. With such a magnetic behemoth, we are truly off the maps of common experience. Such a magnetic field defies easy visualization. If a magnetar were magically brought within half the moon's distance to Earth, its magnetic influence would erase every credit card on the planet and wreak havoc with our electronics. Even much farther away, at distances of tens of thousands of miles, the field could distort atomic structures, tearing molecules apart. Up close, the field is so intense that atoms themselves are stretched and squeezed into thin cylinders. Chemistry as we know it can't operate under those conditions. Fortunately, magnetars reside safely across the galaxy or in distant galaxies, far from our fragile world. Magnetars announce themselves through episodes of violence. Most of the time, a magnetar might be quiet, perhaps detectable only as a faint source of X-rays. But then, without warning, it can erupt. The magnetic field, wound up and stressed within the neutron star, suddenly reconfigures, like a twisted rubber band snapping free. This snap unleashes a tremendous burst of energy. The solid crust of the neutron star, an iron-hard surface under incredible tension, cracks in a starquake. In that instant, a flood of gamma rays and X-rays bursts out. These magnetar flares are among the most luminous events in the universe, short of an outright supernova or the merger of black holes. On December 27th, 2004, Earth was briefly bathed in an extraordinary shower of gamma rays and high-energy photons from across the galaxy. A magnetar, known as SGR 1806-20, had unleashed a giant flare. Even at a distance of about 50,000 light-years, the blast rattled our ionosphere, disrupting communication signals and saturating detectors on spacecraft. For a fraction of a second, this magnetar flare was brighter than anything else in the sky except the Sun. Calculations showed that the magnetar released more energy in that tenth of a second than our Sun emits in 100,000 years. Such numbers boggle the mind. Imagine compressing all the sunlight that falls on Earth for 100 millennia into the blink of an eye. That is the kind of power a magnetar can unleash when it cracks open. What causes such monstrous magnetic fields? Astronomers believe magnetars are born from the deaths of massive stars under very special conditions. When a star, much more massive than the Sun, explodes as a supernova, its core collapses into a neutron star. If the core is spinning fast enough and has certain conditions, it can wind up the magnetic field to phenomenal strength, something like a dynamo effect, writ large by collapse. It's as if a spinning skater pulls in their arms. The rotation speeds up dramatically. In a similar way, the collapsing core's magnetic field becomes incredibly concentrated. The result is a magnetar. These conditions are rare, so magnetars themselves are rare. Out of the thousands of neutron stars known, many observed as pulsars that blink in radio waves, only a few dozen have been identified as magnetars. A newborn magnetar spins extremely rapidly, perhaps hundreds of times per second, and this rotation combined with the intense magnetic field powers its wild behavior. However, magnetars slow down quickly because their magnetic fields sap their rotational energy, converting it to heat and high-energy radiation. Within a mere 10,000 years, a blink of an eye in cosmic time, a magnetar can lose much of its spin. As the magnetar ages, its magnetic field may gradually weaken too. This means magnetars have relatively brief but dramatic heydays. We are fortunate to catch some in the act during this fiery phase, witnessing a star in its most extreme incarnation before it settles down into a more ordinary neutron star. The environment around a magnetar is bizarre. Space near the star is filled with magnetic forces that can accelerate particles to near light speed. The magnetar may be surrounded by a cloud of plasma trapped by its magnetic field lines. When a flare occurs, this plasma is hurled outward at incredible velocities. After a giant flare, the magnetar often emits a series of fainter X-ray or gamma-ray pulses that gradually fade, like the ringing echoes after a colossal bell has been struck. In some sense, we hear the magnetar's quake in these fading pulses as it settles back to an equilibrium. Magnetars have also been suspected to power some of the universe's most puzzling signals: fast radio bursts. These extremely brief but intense flashes of radio energy have mystified astronomers for years. In 2020, a breakthrough occurred when a known galactic magnetar produced a simultaneous X-ray flare and a potent burst of radio waves. This solid link between a magnetar and a fast radio burst suggested that magnetars, even across vast distances, could be responsible for at least some of these enigmatic signals. It appears that the same stress and starquakes that cause a magnetar to emit X-rays can also flick a tremendous pulse of radio energy outward, momentarily outshining entire galaxies in the radio spectrum. It is another reminder that magnetars operate on a scale of power that challenges our imagination. It's humbling to realize that something only about 20 kilometers across, a speck on the cosmic scale, can affect an entire galaxy with its magnetism and outbursts. A magnetar packs more mass than our Sun into a sphere the size of a city, and it threads that sphere with magnetic fields that defy comprehension. If we could safely observe a magnetar up close, we might see little with our eyes. Perhaps it would resemble a small, dense, faintly glowing star. But our instruments would reveal a seething beacon of high-energy light. At unpredictable intervals, it would flare up, becoming for a moment one of the brightest objects in the universe in X-rays or gamma rays, then subside again into eerie quiet. Magnetars carry a certain mystique. For a long time, astronomers knew of their effects before they knew what they were. In the late 1970s, detectors picked up bursts of gamma rays coming from random directions in space. Soft gamma repeaters, they were called. These were distinct from the one-time, extremely powerful gamma ray bursts that we now attribute to distant supernovae or mergers. The repeaters went off again and again from the same spot. At first, nobody knew these were magnetars. Only later did we connect the dots that these must be highly magnetized neutron stars. Now that we know, it's clear we have much left to learn. What exactly triggers a magnetar to flare at a given moment? How does the magnetic energy twist and build up until it catastrophically releases? We continue to watch these stars, catching their spasms and afterglows, trying to decipher the clues they leave about matter under extreme pressures and magnetism beyond anything we can replicate. In the grand scheme, magnetars are short-lived fireworks. Their magnetic fire will gradually dim as the millennia pass, and they will transition into more typical neutron stars, blending into the cosmic background. But while they rage, they remind us of how fierce and strange the universe can be. They are like cosmic volcanoes, dormant for ages, then erupting with catastrophic force. Only instead of molten rock, it's pure radiation that explodes outward, and instead of a mountain's caldera cracking, it's a star's crust tearing under magnetic stress. As we move on from the magnetar's domain, we carry with us an awe for the extremes nature achieves. We have seen stars that feed on others, stars that pulse with cosmic heartbeats, the quiet embers of stars that outlive eons, and now neutron stars that bend the laws of physics with magnetism. Yet, incredibly, the cosmos has more enigmas in store. Not all strange stars announce themselves through dramatic flares or obvious peculiarity. Some are quietly baffling by their very existence. In the next leg of our journey, we will encounter stars that by rights should not exist, stellar outliers that defy the standard stories of how stars are born, live, and die, challenging our understanding of the universe at the most fundamental level. Starlight has guided our understanding of the universe, but some stars seem determined to upend it. They sit as anomalies, whispering that our cosmic textbooks might be incomplete. Through our journey, we have seen general patterns of how stars are born, evolve, and die. Yet here and there, we find stellar outliers that break those patterns, existing when or how they shouldn't. These oddball stars challenge our theories and invite curiosity and wonder. We turn now to these cosmic rebels, the stars that, by all odds, should not exist, and yet they do. In an ancient globular cluster, a spherical swarm of stars that has persisted since the dawn of the galaxy, almost every star is old and tired. These clusters are relics of the early Milky Way, containing stars over 10 billion years old. Most cluster members glow with a reddish or golden light, having long ago exhausted the prime of their youth. Yet hidden among them, a few stars shine with a hot blue-white radiance, as if they were far younger than their neighbours. Astronomers were baffled when they first encountered these blue stragglers, as they came to be called. By all rights, such massive blue stars should have burned out eons ago in a cluster that ancient. They shouldn't exist in that environment. And yet there they were, scattered among the seniors, like youthful gatecrashers at a reunion. For decades, blue stragglers were an unsolved mystery. Only later did we come to understand, as we explored earlier, that they likely steal mass from companions or result from stars merging together, rejuvenating themselves. Essentially, they cheat the stellar aging process by replenishing their fuel. In doing so, these cosmic Peter Pans create an illusion of youth. Blue stragglers, once a perplexing anomaly, turned out not to violate physics after all, but rather to showcase a different path of stellar evolution involving close companions. Yet their presence taught us a valuable lesson. Even in the most orderly, ancient systems, unexpected exceptions can lurk. Traveling farther out into the halo of our galaxy, we encounter a solitary star that holds the nickname Methuselah's star. Catalogued as HD 140283, this unassuming pinpoint of light is one of the most ancient stars ever discovered. When scientists estimated its age by analyzing its brightness and composition, they were startled. Initial calculations yielded about 14 to 15 billion years. That was deeply puzzling, because modern cosmology estimates the universe itself to be about 13.8 billion years old. How could a star be older than the universe? It seemed an absurd result. Something had to be off, either in our measurements of the star or our understanding of the cosmos. This star, in effect, should not exist if it truly exceeded the universe's age. Researchers went back to the data, refining distance measurements, stellar model assumptions, and composition analyses. To make sure, astronomers used precise distance measurements, including observations with the Hubble Space Telescope, to refine the star's intrinsic brightness and thus its age. These careful studies brought the age down a bit, but it still remains on the order of the universe's age, roughly 13.7 billion years, give or take a few hundred million. The paradox of a star, older than everything, was resolved. But the fact remains. This star is incredibly old, formed when the universe was in its infancy. Its very existence takes us back to a time shortly after the Big Bang, when the first generations of stars were forming. It carries only a trace of heavier elements, indicating it was born before the universe had enriched itself much with metals. That a star from such a primordial era is still burning today, and that we can observe it, feels almost miraculous. It's as if we found a still living tree that germinated at the dawn of time. Methuselah's star, quietly shining in our galactic outskirts, reminds us how little we know about the earliest times, and how even our best models must face the test of reality. Not far from the realm of Methuselah's star, astronomers have uncovered other ancient relics with peculiar traits. A few stars have been found with extraordinarily low amounts of heavy elements, even less than Methuselah's star contains. These stars are made almost entirely of hydrogen and helium, the primordial ingredients of the cosmos, with only the faintest sprinkling of heavier atoms. One such star, discovered in 2014, has such a meagre iron content that it set a record. By some estimates, it has only about 1/10,000,000,000th the iron found in our Sun, essentially none at all for cosmic purposes. This star likely formed from a cloud of gas enriched by just a single supernova from the first generation of stars. Finding it was like encountering a living fossil from the dawn of star formation. It taught astronomers that the early universe was capable of forming small, long-lived stars, contrary to the once popular idea that only titanic stars could form initially. The existence of these ultra-metal-poor stars suggests that even among the first stars, some were small enough to survive to the present, or that the second generation of stars could emerge from gas that was only lightly polluted by the first. These ancient wanderers challenge our assumptions about star formation in the early universe. Each one is like a time capsule. Its very chemistry defies what we expected to find, forcing us to refine our understanding of how the elements and stars came to be. If ancient stars can defy age limits, other stars can defy the limits of mass. For a long time, astrophysicists calculated that there's an upper bound to how massive a star can grow. Beyond roughly 150 or 200 times the mass of the Sun, the radiation pressure from the star's light should blow away the surrounding gas, preventing further growth. It came as a surprise then, when observations of a dense young star cluster called R136, nestled in the Tarantula Nebula of a nearby dwarf galaxy, the Large Magellanic Cloud, revealed stars possibly exceeding that theoretical mass limit. One star in particular, known as R136A1, was initially calculated to tip the scales at around 250 solar masses. Later studies adjusted it downward, but it still remains among the heaviest stars known. A star of that heft lives in a state of extreme fury, burning through its nuclear fuel at such a prodigious rate that it will explode as a supernova only a few million years after its formation. But how did it form at all? Such a monster star should not exist, according to earlier models of star formation. Astronomers suspect it might actually be the result of multiple stars merging in the crowded cluster environment, or perhaps an artifact of our view where 2 or 3 stars are so close that their light blurs together. Even so, other individual stars in that cluster clearly tip the scales well above the supposed 150 solar mass cutoff, so the boundary was not as strict as once thought. It seems nature can, under special circumstances, assemble stars of mind-boggling mass. These behemoths live fast and die young, and their existence pushes our theories to the edge. Observing them is like seeing a candle flame 10 times taller than expected. Brilliant, but one wonders how it sustains itself. These outliers show that our theoretical limits are sometimes just guidelines. Rare conditions can push beyond what's typical. Watching these massive stars is witnessing the upper limit of starlight itself, and they certainly defy the usual rules that most stars follow. Stellar oddities aren't confined to birth or longevity. Some even defy the finality of death. One extraordinary star, discovered in recent years, behaved in a way no exploding star was expected to. In 2014, astronomers spotted a supernova, a massive star in a distant galaxy blowing itself apart, and designated it IPTF-14HLs. At first it followed the expected pattern. It brightened to a peak over a few weeks, and then began to fade. But after a couple of months, something astonishing happened. Instead of steadily dimming to darkness, the supernova brightened again. Over the next 2 years, its light rose and fell at least 5 separate times, as if the explosion was restarting or sustaining itself. Such behavior was unheard of. Curious astronomers dug through historical records and found that in 1954, some 6 decades earlier, a telescope had captured another explosion in the same location. It seemed this star had exploded at least once before and somehow remained in existence. Somehow, between that mid-20th century explosion and the one observed in 2014, the star had survived and remained intact enough to explode anew. This defies the standard understanding of a supernova as a one-time terminal event. A supernova is supposed to mark the death of a star, the final grand detonation that leaves behind a neutron star or black hole, or at least disperses the star completely. The star in question, however, seemed to be a zombie star, refusing to die despite undergoing cataclysm after cataclysm. The leading hypothesis is that this star is undergoing a pulsational pair instability supernova, a rare, long-theorized process. In a star perhaps over 100 times the Sun's mass, the conditions in the core can create bursts of thermonuclear fury that don't destroy the star outright, but blow off its outer layers. The star survives the blast, only to rebuild and explode again in cycles, until one final eruption ends it. It's a kind of stellar death by installment plan, rather than a single cataclysm. What was once purely theoretical now had a potential example in IPTF-14HLs. Observers were astonished. It was like witnessing a cosmic phoenix, a star rising from its own ashes repeatedly. This star that wouldn't die is a vivid reminder that even in well-trodden territory like supernovae, nature can devise more complex narratives than we imagined. Not all stellar oddities are so dramatic in their actions. Some are quietly confounding because of what they contain. Consider the case of Przybylski's star, an otherwise unremarkable-looking star of moderate size that has become legendary among astronomers for its bizarre chemical composition. When scientists spread its light into a spectrum to discern its chemical makeup, they found a bewildering forest of spectral lines corresponding to elements seldom seen in stars. Not just rare elements like platinum or gold, but exotic, short-lived isotopes that should not persist in a stellar atmosphere. Lines of europium, gadolinium, and dysprosium, rare earth metals, stood out. Even technetium and promethium appeared to be present, elements which have no stable forms and normally vanish quickly after they're created. Such elements are virtually absent in ordinary stars, making Przybylski's spectrum akin to a coded message in exotic matter. According to standard stellar evolution, these substances should have decayed into more common elements long ago, or never been there in the first place. The star's peculiar spectrum raised wild ideas. Could it be continuously generating these elements through some unknown internal process? Does it harbour unusual nuclear reactions, or a stash of freshly made radioactive material? At one point, some even half-jokingly speculated about advanced aliens dumping their atomic waste into the star, or using it as a beacon by loading it with specific isotopes, a testament to how puzzling the data was. More grounded theories suggest that the star's intense magnetic field, Przybylski's star, is a type of star known for strong magnetism, might be sorting elements in its atmosphere, or perhaps it's producing unusual nuclear reactions in localized spots near its core. There's even the notion that unknown ultra-heavy elements could be forming and then decaying into the weird mix we see. To this day, no fully accepted explanation exists. Przybylski's star remains a cosmic curiosity, quietly shining in the constellation Centaurus, its light offering a chemistry lesson from beyond the periodic table, one that defies the normal rules of stellar makeup. The strangeness continues when we look at how some stars behave in terms of their brightness. Earlier, we encountered stars that pulse regularly, but there are stars that dim and brighten in patterns that make no sense for normal stellar variation. One star in particular made headlines for its baffling light curve. Tabitha's star, more commonly known as Tabby's star, named after Tabitha Boyer-Gian, the astronomer who led its study. Discovered in data from NASA's Kepler Space Telescope, this ordinary-seeming star would sporadically dip in brightness by significant amounts at irregular intervals, without the telltale periodicity of a planet passing in front of it. Some of the dips were huge. Up to 15% or 20% of the star's light would vanish, far more than any known planet could cause, and the dimming might last days or weeks. The timing of the dips was irregular, with no stable cycle to count on. For years, telescopes watched Tabby's star and recorded these unpredictable plunges. It was unlike any eclipsing binary or known variable star pattern, and we had simply never seen a star do this. For a while, every possible explanation struggled to account for the observations. Dust clouds, swarms of giant comets breaking apart, a ring of debris warped around the star. Each idea had issues. The star did not show the expected infrared glow of large amounts of dust, for example, and the pattern of dimming did not match a one-time collision or breakup. In the midst of this, a more fanciful idea captured the public's imagination. Perhaps the dips were caused by a gigantic artificial structure, an alien megastructure, orbiting the star and occasionally blocking our view. While mainstream scientists viewed this as an unlikely speculation, its mention showed just how unprecedented the star's behavior was, something never observed before, prompting even far-out ideas to be considered. Teams of astronomers, professional and amateur alike, banded together to monitor Tabby's star around the clock. They sought clues such as color changes during dips, since dust tends to dim blue light more than red, and any periodicity hiding in the data. Over time, evidence emerged that at least some of the dimming could be due to sheets of dusty material, perhaps in a tilted orbit, or from the aftermath of a shattered exomoon or disrupted comet swarm. The star also was found to be slowly fading over decades, which complicates the puzzle further. The consensus leans toward a natural explanation involving dust, but no single theory yet accounts for all the observed behavior. To this day, Tabby's star remains an outlier. It reminds astronomers that even a seemingly normal star can exhibit phenomena we never anticipated. It keeps us humble and alert to the cosmos's capacity for surprise. Even relatively nearby, in our own galaxy, nature holds secrets that can leave us scratching our heads. Perhaps one of the most mind-bending stellar oddities is a star that contains another star, a so-called Thorne-Jitkov object. Imagine a red supergiant star, swollen and cool, which has somehow swallowed a neutron star into its core. Theory holds that if a neutron star, the dense remnant left after a supernova, gets engulfed by a giant star, it could take up residence in the giant's center rather than simply destroying both. The neutron star would settle into the core and act like an insanely hot, dense engine inside the larger star, potentially altering the big star's structure and behavior. Thorne-Jitkov objects were predicted decades ago as an exotic possibility, but for a long time, they were purely hypothetical. Then, a few years ago, astronomers announced that a peculiar red supergiant star in the Small Magellanic Cloud, a neighboring dwarf galaxy, had unusual chemical signatures, particularly certain elements in odd abundances, that might be explained if a neutron star were lurking inside it. Those signatures matched predictions for a Thorne-Jitkov object, where unusual fusion processes could occur in the shell of gas around the embedded neutron star. If this discovery holds up, it means literally a star that shouldn't exist according to normal stellar evolution. A star with another star inside it, a cosmic Russian doll. It would be a fleeting, rare state. Eventually the neutron star would either fully merge or the giant's envelope would dissipate. But the fact that nature might allow it at all is astonishing. It's a reminder that sometimes stars can undergo very strange interactions and end up in configurations not easily imagined, hybrid objects that straddle categories. From stars that refuse to age or die on schedule, to those that form with impossible masses or bizarre compositions, these outliers expand our sense of what is physically possible. Each time, astronomers think they have a handle on the life story of stars, the universe hands us a counterexample that says, nature is more inventive than you thought. These odd stars are not mere curiosities. They often point toward new physics or overlooked processes. They show that the story of stellar evolution has many chapters, some common, some rare, and full of twists. It's as if the cosmos writes most stars along a standard script, but occasionally scribbles a surprise ending or an unexpected chapter. Encountering these misfits of the stellar world fills us with wonder. It's as though the universe keeps a few trump cards up its sleeve, revealing them only when we look closely or happen upon them by chance. These stars might be few in number, but they loom large in significance, because studying them teaches us so much. We learned about mass transfer and binary evolution from blue stragglers. We refined cosmic age estimates with Methuselah's star. The star that wouldn't die gave evidence for new kinds of stellar death throes. The puzzle of chemically peculiar stars like Przybylski's challenges our understanding of nuclear processes. Each discovery of a star that shouldn't exist forces us to question whether our theories are complete or whether some new phenomenon, some missing puzzle piece, is at play. As we come to the end of this exploration of stellar oddities, the cosmos continues to surprise. We have delved into stars that steal life from others, stars that pulse with steady or chaotic rhythms, white dwarfs that persist for trillions of years, neutron stars that unleash magnetic fury, and stellar outliers that rewrite the rules. Yet, beyond the realm of stars, lie even stranger phenomena. There are invisible forces and dark mysteries that govern the cosmos, and exotic endpoints of matter where our intuitions falter. If stars themselves hold secrets, the broader universe holds many more. Our journey will carry us from the stellar realm into these deeper cosmic mysteries, continuing our quest to illuminate the unknown. The universe still has more strange secrets to reveal, and we journey onward, ever curious, into the next chapter of discovery. A pale sky begins to brighten over the horizon of an alien world. Not one, but two suns are rising. One star is a golden white orb, slightly larger, the other a smaller orange companion. They climb together, casting twin dawns across a strange landscape. Two sets of shadows stretch across the ground, overlapping in a dance of light. This is a world with two suns, a circumbinary planet, where daylight comes from two different stars at once. The scenery bathed in dual sunlight is surreal. Colours are richer and more complex under the mixed hues of two stars. When both suns hang in the sky, there are no truly dark shadows, for each star fills in the other's light. It is a perpetual balancing act of day and dusk, as the stars circle each other and trade places in the heavens. Life under twin suns would experience a very different rhythm than life on Earth. Days on this planet are defined not by the rising and setting of a single sun, but by the intricate dance of two stellar partners. Sometimes, both suns set at nearly the same time, and nightfall brings an abrupt darkness, deeper than any on Earth. But those nights are rare and precious. More often, one sun will still be up while the other has already set, providing a continued, softer illumination. True night, when the sky is free of any sun, might only come during special alignments, perhaps when both stars dip below the horizon together or eclipse each other. Imagine a sunset where the first sun descends in a blaze of orange, and just as its light fades, the second sun is still hanging above, painting the landscape in a gentler glow for hours longer. Only when that second star finally sets does the sky slip into twilight and then darkness. Creatures on such a world might evolve eyes or daily cycles attuned to this complex schedule, perhaps active under the bright, dual daylight and the extended twilights. The sky on a twin sun planet is a celestial stage with two performers. At times, the two suns might appear close together, rising as a pair in the same part of the sky. Other times, they could be on opposite sides of the firmament, one rising as the other sets, giving the planet a double dose of daylight on different horizons. The colour of each sun could be different, one star's light tinging the clouds a warm yellow, while the other's adds a coppery hue. Sunrises and sunsets would come in an array of combinations. Dual sunrises, where two dawns colour the sky at once, or staggered sunrises, where one star creeps above the horizon shortly after the other, prolonging the morning glow. Imagine the spectacle of a double sunset, one star dipping below the horizon igniting the clouds with pink and gold, while the second star still hovers above, casting long purple shadows until it slowly fades away. The beauty would be both familiar and eerily alien. For any inhabitants or life forms, the concept of a day might be very different. Perhaps they have no word for night in the way we do, because complete darkness is so seldom. Plants might have adapted to two sources of photosynthesis, maybe evolving pigments that can handle the broad spectrum of dual sunlight. On a world with a red dwarf sun and a blue-white sun, for instance, vegetation could be a mix of colours to absorb both red and blue light efficiently, deep black foliage or shimmering iridescent leaves that shift tone depending on which star's light is dominant. The circadian rhythms of animals could be complex. Imagine creatures that nap during the brief, true nights, but also seek shelter during periods of intense double noon when both suns high overhead make the world uncomfortably bright and hot. Conversely, when one sun sets and only a single sun remains, those creatures might become more active, sensing the partial relief as the light dims slightly. Astronomers have long wondered whether planets could stably orbit two stars, and now we know they do. The first such circumbinary planet discovered was a gas giant world. It was found by the Kepler Space Telescope, confirming science fiction visions of twin-sunned planets like the legendary Tatooine. Since then, several have been found. Planets circling pairs of stars, their orbits wide enough to encompass the binary dance of their suns. These planets experience the gravitational pull of not one, but two stars, yet they manage to maintain a steady path, usually orbiting around the combined center of mass of the star pair. From the planet's perspective, its two suns typically stay relatively close together in the sky, because the planet is far away compared to the separation of the stars. But if those stars eclipse each other as seen from the planet, there could be moments of strange twilight, when one sun passes in front of the other and dims its light. The climate on a twin-sun world might also be unique. When both suns are up, the influx of energy is greater, potentially making midday very warm, especially if the stars are of comparable brightness. The planet could have blistering periods when two suns beat down at once. Yet when one sun sets, a noticeable cool-down might occur, even though it's still technically day under the remaining sun's light. Seasons could be influenced by the orbits of the stars as well. If the two suns have an eccentric orbit around each other, there could be times when they are closer together and times when they are farther apart, changing the overall sunlight the planet gets over years or decades. Imagine a double summer, when a planet receives the full blaze of a near alignment of both stars on the same side of the sky, versus a double winter, when the stars are spread far apart, or one star is hidden behind the other for a stretch. Such patterns would add another layer of complexity to how life and weather adapt on these worlds. From the surface, living under two suns might feel like living with two clocks in the sky. The two suns rise and set in a pattern that repeats predictably, but is longer than a simple day. Perhaps the planet's rotation doesn't match the binary star's orbit period, leading to shifting cycles where sometimes the stars line up and other times they are opposed. There could be a long cycle, maybe lasting many of the planet's rotations, after which the pattern of double sunsets and staggered dawns repeats. Early astronomers on this world would notice a complex dance in their heavens. Their version of calendars might be based on the interplay of two suns, tracking when both will be above the horizon or when their eclipses occur. This dual sun cycle would define their concept of time and seasons. If such a planet lies in the habitable zone, the right distance for liquid water, one can only wonder what evolution might produce under two-star conditions. Would life find the double sunlight a boon, growing faster with two sources of energy? Or would the extra radiation and complicated day-night cycle favor creatures that are more adaptable and flexible? Perhaps on a twin-sunned oasis, you might find forests of hardy plants that close some of their leaves when both suns are high to avoid overexposure, and open them during gentler single-sun periods. Nocturnal creatures might scarcely exist, replaced by solsternal creatures that come out when only one sun is up, in the softer half-light. The mythology and culture of any intelligent beings might revere the two suns as a dual deity, two fiery eyes in the sky watching over their world. As we watch this wondrous planet with two suns in our imagination, it's clear that nature's creativity knows no bounds. Double sun worlds expand our concept of what a sky can look like. Standing on such a world, you could watch two starry disks light up the sky together, or see two overlapping coronas during an eclipse. Yet even this exotic arrangement is part of the universe's tapestry. Planets will form and life will strive wherever it can, under one sun or two. Our voyage now takes us onward, leaving behind the twin sunsets of these binary star worlds. Beyond even the strangest skies lie planets that redefine what a world can be made of. In the next leg of our journey, we will encounter planets of diamond and metal, exotic compositions far from Earth. We will marvel at how diverse and surprising the materials of planets can be. Take, for example, the idea of a diamond planet. Astronomers have identified one candidate orbiting a pulsar, the remnant core of a star, about 4,000 light-years away. This planet is believed to be the carbon-rich husk of a once sun-like star, compressed to incredible density. Under such pressure, carbon could crystallize into diamond. Picture a world, perhaps the size of Earth, but far heavier, with much of its interior one enormous diamond crystal. Its surface might not shine like a gemstone. More likely it's cloaked in a dull grey mantle of carbon and graphite. But if you could peer inside, you'd see a brilliant lattice of diamond extending for thousands of kilometers. It's a planet literally made of crystal, the result of nature's high-pressure alchemy in the aftermath of a supernova. On the surface of this diamond planet, the landscape would be alien and dark. The planet orbits a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. There is no gentle sunlight here. Instead, the sky might flash with the quick pulses of the neutron star's energy. The ground underfoot could be hard carbon, with mountains of graphite and diamond beneath a thin crust. If you struck a hammer to the ground, the sound might ring with a high bell-like tone, as the material is so incomparably rigid. It's a world that was born in violence and then frozen into a crystal calm. We can scarcely imagine walking on terrain where an entire mountain might be a single giant diamond in structure. Not all exotic planets are dark and cold, however. Consider another kind of world, a planet made mostly of metal. Our own Mercury is a tiny hint of this category, a planet with an oversized iron core. But elsewhere, there are super-Mercuries, larger worlds with even greater metal content. One such planet, discovered around a nearby star, is so dense that scientists infer it must be primarily iron. It might be the exposed core of a once bigger planet. Perhaps long ago, two planets collided, stripping away the outer layers of one and leaving behind a ball of metal. Now that iron planet orbits close to its star, seared by heat, its surface could be a vast expanse of iron and nickel, possibly coated in a thin veneer of rock that survived. In places, that rock might have melted into seas of lava under the star's intense glare, exposing shiny metal plains between them. Standing on a metal world, you would be treading on ground that is akin to the core of Earth itself. The gravity would likely be strong for the planet's size, given all that heavy iron packed beneath your feet. If the planet is hot, and many metal-rich planets orbit very close to their stars, you might see the horizon glowing where metal vapor is lifting off the overheated surface. Iron-rich clouds could form in the thin atmosphere during the day, only to rain droplets of molten iron back down during the cooler twilight. Imagine the weather on such a planet. Iron rain sizzling against iron ground, the air tinged with the smell of hot metal. It's a far cry from the water cycle of our homeworld. How would a planet of mostly iron appear from space? Perhaps as a dull, grey-brown orb, not particularly reflective, unless volcanic activity periodically reveals fresh metallic expanses. Without a thick atmosphere or oceans, its surface features would be craters, cliffs, and cracks. A bit like Mercury's appearance, but even more barren. If the star's light glints off a freshly exposed metallic plain, or a river of cooling iron lava, it might sparkle briefly. Generally, though, these metal planets would look unassuming, belying their tremendous density. A chunk of such a planet the size of your fist would weigh far more than a typical rock. It would be like holding a piece of a planetary core. Some planets might be metal and diamond combined. Imagine a massive iron core wrapped in a mantle of carbon. If such a planet formed around a star rich in carbon, its rocks would be made of carbides, and under high pressure, those could crystallize into diamond pockets inside a metallic crust. The variety is astounding. One star's debris might build a planet mostly of quartz and glassy silicates, while another's could build one dominated by shiny metals or sapphire-like crystals of aluminum oxide. Nature shows that if the conditions are right, almost any solid material can become the foundation of a world. The story of how these exotic planets come to be is as fascinating as the worlds themselves. A diamond planet might begin as part of a binary star system. One star dies and sheds its layers, and its carbon core survives as a planet orbiting the dense neutron star left behind. A metal planet might be the aftermath of a cataclysm, a collision so immense that it blasts away the lighter crust and mantle, leaving only a metallic heart. Or it could be the evaporated remnant of a giant world that ventured too close to its sun, its atmosphere and outer layers boiled off until only an iron-rich core remained. In our quest to find the most unusual planets, these diamond and metal worlds serve as shining examples of nature's extremes. They remind us that not all worlds are like Earth, or even like the familiar planets of our own solar system. Some are forged in catastrophic events. Others are molded in chemical environments very different from our own. Each one expands our understanding of what is possible in the cosmos. As we imagine standing on these alien terrains, amid the glow of a neutron star, or under the metallic skies of a sun-scorched iron world, we stretch the definition of what a planet can be. Our journey through the universe's strangest secrets has taken us from lava oceans to rogue planets adrift in darkness, from ice giants with diamond rains to twin suns setting in tandem. Each step revealed new wonders and extremes of nature's creativity. Having explored these extraordinary worlds, we carry with us a profound sense of awe. The cosmos is richer and more surprising than we ever imagined, and there are always more secrets waiting to be revealed. As our journey continues, we drift deeper into the cosmic ocean of mysteries. In the distance, faint whispers ride on invisible waves, fleeting bursts of radio energy from far beyond our galaxy. These are fast radio bursts, or FRBs, millisecond-long flashes of radio waves that fire off and vanish almost as soon as they're noticed. First discovered in 2007, they arrived unannounced in data meant for other studies. In that initial detection, a single, ultra-brief radio pulse from the depths of space blazed with an intensity that defied belief. In the blink of an eye, it unleashed as much energy as the sun emits in 3 full days. A cosmic flashbulb popping somewhere in the dark reaches of the universe. This astonishing burst, so powerful it outshone every known radio source of the time. Left astronomers in awe and confusion. Here was a phenomenon that seemed to shout across billions of light years, yet nobody knew what had spoken or why. For years after that first burst, the skies fell quiet again. No similar signals were seen, prompting some to wonder if the original detection had been a fluke or an illusion. But gradually, the sky's silence broke. More of these erratic radio flashes began to appear, one by one, then by the dozens. Today, telescopes have catalogued hundreds upon hundreds of FRBs, scattered all over the sky. And still, this might only be a glimpse of the true abundance. By some estimates, several of these bursts may be going off every minute across the cosmos, unnoticed by us. Imagine that. Countless hidden fireworks in the radio spectrum, popping off in distant galaxies, while we catch only a lucky few. They are mysterious signals from deep space, emitting mind-boggling amounts of energy. Brief cosmic crackles that outshine stars and then disappear. Each one is a puzzle piece from an unknown picture, teasing us with its energy and elusiveness. At first, scientists assumed these bursts were one-time cosmic events, catastrophic happenings that occur, flash, and never repeat. After all, early searches failed to catch any source flaring twice. An FRB was thought to be like a solitary lightning bolt in a clear sky. Startling, but never striking the same place again. And indeed, initial follow-up observations of known FRB locations yielded nothing but silence. Then, in 2016, a surprise changed everything. One of the known FRB sources suddenly lit up again, repeating its flashes as if sending multiple messages. This repeater, labelled FRB12102, proved that whatever was producing these bursts could do so more than once. The source unleashed burst after burst, and it wasn't alone. We now know a fraction of FRBs do repeat in this way, perhaps 3 to 10% of them, while the rest remain stubbornly one-off. Why some of these cosmic signals are single, isolated screams, and others stutter in repeated cries, is yet another layer of the mystery. Each new observation forces us to reconsider what engines could be powering these cosmic sirens. Speculation has run wild in the face of such unknowns. Astronomers, with imaginations fired by the extremes of nature, have proposed all manner of possible origins. Could they be the death cries of colliding black holes? The last gasps of stars ripped apart by magnetically twisted neutron stars? Some even playfully wondered if they might be interstellar beacons, perhaps advanced civilizations testing powerful transmitters, though no evidence truly points that way. In one amusing twist, a few FRBs detected in early data turned out to be earthly in origin. The microwave ovens at a telescope facility opened at just the wrong moment, mimicking a cosmic signal. But within the genuine celestial bursts, patterns began to emerge. The leading theory soon centered on one of the universe's most extreme objects, magnetars. These are neutron stars, the ultra-dense, city-sized remnants of supernova explosions, with magnetic fields so intense they boggle the mind. A magnetar's magnetic field is trillions of times stronger than Earth's, powerful enough to distort atoms and unleash enormous energy. If anything in nature could create a flash as intense and brief as an FRB, a magnetar seemed a prime candidate. Evidence for the magnetar idea grew in 2020, when a remarkable stroke of luck occurred. In April of that year, a magnetar in our own Milky Way galaxy suddenly erupted with a flare of X-rays, and at the very same moment, radio observatories caught a fast radio burst from that direction. It was a cosmic simultaneous flash. High-energy X-rays and a radio burst, hand in hand. For the first time, scientists directly linked an FRB to a known object, a magnetar about 30,000 light-years away. This event proved that magnetars can produce FRB-like signals, at least under the right conditions. It was like finding a single clue that suddenly makes a suspect in a mystery all the more likely. Magnetars, born in the explosive deaths of massive stars, have volatile surface fields that can crack and quake. Perhaps in those moments, they emit an intense burst of radio energy, a quick crack of thunder following the starquake. Supporting this notion, most FRBs we've traced to specific galaxies tend to come from places where stars are being born rapidly. Those are exactly the kind of galaxies where young, massive stars would have lived fast and died young, leaving behind fresh magnetars. It all seems to fit. Mostly. Yet even here, the universe resists giving up all its secrets. Just when scientists felt they might be homing in on an answer, new observations added more intrigue. In one case, an FRB was pinpointed not in a bustling star-forming region, but on the outskirts of a galaxy, in an ancient cluster of old stars. Finding an FRB source in a globular cluster, an unlikely place with no young stars to make magnetars, was a curveball. It kind of challenges the magnetar progenitor idea, one astronomer remarked, since a globular cluster's stars are all old and long settled. If no new magnetars are being born there, what could be triggering such a burst? Perhaps, researchers speculate, magnetars can form in unexpected ways. Maybe two old neutron stars in those clusters spiral together and merge, suddenly creating a brand new magnetar that then erupts with radio waves. Or perhaps a white dwarf star accretes matter until it collapses, another path to produce a magnetar later in life. These outlier events hint that FRBs might not have a single explanation. There could be multiple kinds of cosmic engines, some young, some old, that all produce similar flashes. It's a sobering reminder that even as patterns emerge, the full story of FRBs is far from clear-cut. Picture the scene. Deep in the quiet of a distant galaxy, something suddenly releases a tremendous jolt of energy. Radio waves surge outward in a millisecond blast, spreading across space for billions of years. Eventually, a tiny, whisper-faint fraction washes over Earth. Our radio telescopes, patiently staring at the sky, register a sharp spike. And then it's gone. The whole event is over almost before we know it, leaving only questions behind. Where did it come from? What could possibly be so powerful, yet so brief? These questions drive a worldwide effort to capture more FRBs and decode their origin. New telescopes and arrays are coming online, scanning wide swaths of the sky every night for those telltale millisecond flares. Each detection brings the hope of finding patterns, perhaps a repeating rhythm, or a clue in the radio frequency that might distinguish a magnetar flare from some other exotic cause. Even now, FRBs remain one of astronomy's most beguiling unsolved mysteries. They are among the greatest cosmic enigmas of our time, a cosmic puzzle scattered across the universe, pieces falling down to us in the form of these strange bursts. With each passing year, technology improves, and we gather more pieces. Thousands of FRBs have been logged, and more are detected every week as instruments like Canada's CHIME telescope tirelessly watch the sky. CHIME, for instance, can catch a few FRBs each day, vastly outpacing older surveys. It's being upgraded to pinpoint where these bursts originate with far better accuracy. Meanwhile, the upcoming square-kilometre array, a giant observatory spread across continents, promises to find even fainter and more distant bursts by the dozens or hundreds. With every new detection, astronomers rush to follow up, aiming larger radio dishes, optical telescopes, even X-ray and gamma-ray observatories at the spot, hoping to glimpse whatever lingers after the flash. In rare cases, a faint nebula or a persistent radio glow is found at an FRB's location, giving away a host galaxy or a source that can be studied further. Those precious few identifications are like lanterns in the dark, illuminating the environments that birth these bursts. What have we learned so far? We know FRBs come from far outside our Milky Way. Most are billions of light years away, meaning they erupted when the universe was younger, and their light travelled for eons to reach us. We know they can outshine whole galaxies for the briefest of moments in radio energy. We suspect strongly that magnetars are involved in at least many of these events, especially given the Milky Way magnetar connection and the prevalence of FRBs in young galaxies. But we also see hints that not all FRBs fit the same mould, that some may arise from scenarios we haven't yet imagined. It's a bit like hearing echoes in a vast cavern and trying to map the unseen chamber from the sound. Each echo tells us something, but the full shape still eludes us. The universe, it seems, isn't giving up its secrets just yet. Listening to these cosmic radio flashes has a strangely poetic quality. They are so brief and faint by the time they reach us, yet they carry the energy of gigantic events. Each one is a hello and goodbye from some far-flung corner of the cosmos. In a way, catching an FRB is like intercepting a cosmic postcard with no return address. Just a quick note that says, "Something astonishing happened here," and nothing more. Decoding those notes is the task at hand for astronomers around the world. With every new burst detected, they triangulate its position, measure its dispersion, how the high and low radio frequencies arrive slightly smeared out, which tells us how far it travelled through intergalactic plasma, and try to trace it to a host galaxy. Piece by piece, the story is unfolding. One day, perhaps in the not-too-distant future, we'll have a clear answer to what these fast radio bursts truly are. We might find that they were the shouts of newborn magnetars all along, or a mix of different cosmic phenomena. Or perhaps the solution will be something no one predicted, a brand new astrophysical phenomenon that will expand our understanding of high-energy physics. For now, FRBs continue to ring out their cosmic alarms at random, keeping astronomers alert and the rest of us filled with wonder. The mystery of these fleeting, powerful signals from deep space deserves to be solved. As one researcher said, and solving it will likely reveal new insights into the behavior of matter and magnetism under extreme conditions. It might even open a window into events we've never directly witnessed, like the formation of a neutron star or the collision of exotic stellar remnants, since FRBs could be the first sign of those distant catastrophes. So we keep listening. We keep watching the skies with patient curiosity. Each enigmatic burst reminds us that the universe still holds surprises that can arrive without warning, even in the quiet emptiness between the stars. Yet, mysterious as they are, Fast radio bursts are not the only puzzling phenomena whispering to us from the depths of space. Not all cosmic enigmas come in the form of light or radio waves. Some come crashing down upon us as particles, tiny messengers carrying enormous energies, striking our world from above. With the gentle patter of cosmic rain, another mystery unfolds. High-energy cosmic rays, those invisible bullets from the far universe that hit Earth's atmosphere with energies that baffle our understanding. Just as FRBs are whispers in the dark, cosmic rays are like cosmic raindrops, some so powerful they defy what we thought nature could do. Let us turn now from waves of light to these speeding particles that arrive from the stars, as we continue our exploration of phenomena that defy understanding. We lift our gaze to the night sky, but this time we imagine not the light that comes down, but the unseen shower of particles that constantly rain upon us. Every second, Earth's atmosphere is struck by subatomic particles traveling at near light speed, shed by the sun, distant stars, and more violent sources. Most are modest in energy, the sun's solar wind or the debris of supernovae. But every so often, detectors on Earth register something extraordinary. A single atomic particle, perhaps a proton or a nucleus, barreling in with an energy that stretches the limits of known physics. These are cosmic rays with impossible energy, particles so swift and potent that when they collide with our atmosphere, they create cascades of secondary particles and light that spread like a giant cosmic firework above the clouds. To encounter one is exceedingly rare. An ultra-high-energy cosmic ray might strike a single square kilometre of Earth only about once in a century. But they have been observed, and their existence poses a profound riddle. What natural engines can hurl a single proton to such fantastic speeds and energies? The poster child of this mystery arrived on the night of October 15th, 1991, when an experiment in Utah detected an event so shocking that the physicists who saw it literally dubbed it the "oh my god" particle. This one proton, or perhaps the nucleus of an atom, slammed into the atmosphere with an energy of about 3 × 10⁻20 electron volts. In more familiar terms, that's roughly equivalent to a baseball travelling at about 100 kilometers per hour. But all of that energy was carried by something no bigger than a subatomic particle. Imagine a single proton, invisible to the eye, hitting the air above us with the punch of a well-thrown fastball. It's almost inconceivable. The "oh my god" cosmic ray was more than 100 million times more energetic than the protons we accelerate in the largest human-made particle colliders on Earth. It was as if nature had built a particle accelerator, vastly outperforming anything our technology can achieve, and then flung a particle straight at our planet. For years, the "oh my god" particle stood alone as the most energetic cosmic ray ever seen. It provoked intense speculation. Where could it have come from? At such extreme energies, even the vast distances of intergalactic space pose a problem. There's a limit known as the GZK cutoff, which suggests that ultra-energetic protons will gradually lose energy by interacting with the faint afterglow of the Big Bang, the cosmic microwave background radiation, as they travel. By rights, a proton with the energy of the "oh my god" particle shouldn't be able to come from extremely far away. The thinking goes that it would have been slowed down by those interactions if it had travelled hundreds of millions of light years. So perhaps it was spawned relatively nearby, in cosmological terms, somewhere in our corner of the universe. But when scientists tried to trace the arrival direction of this singular particle back to a source, no obvious culprit lay in its path. It seemed to come from a direction in the sky that is fairly unremarkable. Certainly no extremely active galaxy or blazar, a galaxy with a feeding black hole jet pointed our way, was in that exact line of sight. The mystery only deepened. the most powerful particle ever seen, and we had no clue which cosmic accelerator shot it at us. Over the years, a few more of these ultra-high-energy cosmic rays have been recorded, though none quite match the drama of the oh my god particle. In 2021, for example, an event was detected with energy around 240 exa electron volts, 2.4 by 1020 eV, nearly as extreme. Once again, scientists scrambled to identify its origin. An international array of detectors in Utah, known as the telescope array, picked up this particle and calculated the direction it came from. They mapped its path through the cosmos, correcting for the way interstellar and intergalactic magnetic fields might have bent its trajectory. For charged particles do not travel in straight lines through space. They are nudged and wiggled by magnetic fields like a boat by ocean currents. After accounting for these deflections as best as possible, the path pointed to nothing. More precisely, it pointed toward a patch of sky relatively empty of notable galaxies, a cosmic void. Efforts to find the particle's birthplace led scientists to a mostly empty stretch of space. This was baffling. The prevailing thought is that only the most extreme environments can accelerate particles to these energies. Candidates include things like the hot, tumultuous regions around supermassive black holes, especially active galactic nuclei with powerful jets, or perhaps hyper-energetic shockwaves in certain starburst galaxies where many supernovae are colliding with stellar winds. Some even speculate about exotic sources like the decay of primordial cosmic strings or other relics of the Big Bang, though evidence is scant. But the one thing they all have in common: they should occur in places with lots of matter and activity, not in vast voids devoid of galaxies. So how could a particle come from nowhere with such energy? One possibility is that there is an active source near that direction, but hidden from our view. Perhaps a faint, distant quasar, or a radio galaxy jet that hasn't been identified yet. It could also be that the magnetic deflection is trickier than we think, and the particle's true origin is a little offset from where the simple backtracking suggests. However, it underscores a key challenge. These ultra-high energy cosmic rays, UHECRs, as scientists call them, are extremely rare and hard to pin down. By the time they reach us, they've been traveling for ages, and their paths have been twisted by magnetic fields in the Milky Way and beyond. It's as if you found a message in a bottle washed up on the beach. You might discern the ocean it came from, but the exact island of origin remains elusive, because currents have carried it far off course. Similarly, the magnetic currents of space scatter the incoming directions of cosmic rays. So we detect them arriving from somewhere not directly pointing back to their source. To put into perspective just how extreme these particles are, consider this. If you add up the energy of all visible light from a bright star, or even an entire galaxy that's spread out over many photons, here we have single particles carrying macroscopic amounts of energy. The oh my god particle's energy, about 50 joules, might sound small in everyday terms, roughly the kinetic energy of a flying tennis ball, but for one proton, it's almost unfathomable. Normally, at everyday energies, a proton's energy is minuscule. Even in the Large Hadron Collider, we accelerate protons to about 7 trillion electron volts, 7 pi 10 and 12 eV per proton. The oh my god particle was 50 million times more energetic than that. It challenges our understanding of acceleration mechanisms. How do you get a charged particle to such a speed? It likely requires a cosmic accelerator of immense scale. Perhaps an enormous shockwave in intergalactic space, driven by colliding galaxy clusters, could do it. Or the fierce electric and magnetic fields near a supermassive black hole's relativistic jet might sling particles out at near light speed. The favoured explanation for these most energetic rays is that they originate outside our Milky Way, in violent cosmic environments, like the jets of giant black holes or the turbulent cores of starburst galaxies. In those places, natural particle accelerators, electromagnetic shock fronts, twisting magnetic funnels can, in theory, boost particles to extraordinary energies. Even then, there's a limit, because as mentioned, if the sources are too far away, those particles should lose energy en route by interacting with the cosmic microwave background, CMB. This CMB is a bath of low-energy photons that fills space, a relic of the early universe's afterglow. A proton barreling through that sea at near light speed will occasionally hit a CMB photon and produce a reaction, bleeding off some energy. The expectation is that beyond roughly 150 million light-years, space becomes a hindrance to the highest energy particles. Thus, the puzzle. We see these ultra-energetic cosmic rays, but no obvious source within that kind of distance in some cases. It suggests either that our understanding of the energy loss is slightly off, or the sources are relatively nearby but not easily seen, or, and this is more speculative, that new physics might be involved. Perhaps the particle was not a proton, but something even more exotic that interacts differently. Some have wondered about heavier nuclei, or even particles outside the standard model of physics. When these rare supercosmic rays collide with our atmosphere, they create spectacular cascades of secondary particles. High above us, the single proton strikes a molecule of air and shatters it, producing pions, muons, electrons, and gamma rays in a big subatomic shower. Those products, in turn, smack into other air molecules, multiplying the cascade. By the time this particle shower reaches ground detectors, it can spread over many square kilometers, with billions of secondary particles raining down. Modern observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in the United States consist of grids of detectors spaced out over large areas, designed to catch these extensive air showers. From the pattern of arrival times and energies across the detector network, scientists can work backward to estimate the energy and incoming direction of the original cosmic ray. It's a bit like hearing a distant thunderclap echoed across a mountain range. By timing the echoes, you deduce where the lightning struck and how strong it was. Through such techniques, we have confirmed that the highest energy cosmic rays do indeed come from outside the Milky Way. They're not just the output of some unusually energetic pulsar or supernova in our own galaxy. Our galaxy provides plenty of cosmic rays, but at much lower energies on average. They seem linked to extragalactic phenomena. One clue emerged in 2017 when researchers found that the arrival directions of many UHECRs were not uniformly spread across the sky, but showed a slight concentration toward the direction of certain large-scale structures, like the supergalactic plane, hinting that the distribution of nearby galaxies might be involved. This suggests that perhaps clusters of galaxies or massive black holes in relatively close galaxies, within a few 100 million light-years, could be sources. Still, individual events like the 1991 and 2021 particles remind us that specifics are hard to pin down. The existence of these impossible cosmic rays has practical implications too. They tell us that nature is accelerating particles to energies far beyond our capabilities, which means there are astrophysical processes out there reaching energy regimes we've never tested in laboratories. In a sense, each ultra-high energy cosmic ray is a tiny probe, a test particle that has experienced extreme conditions. By studying them, we might glean information about those extreme environments. They might carry information about magnetic fields in distant galaxies, or clues about interactions at ultra-high energies. For example, how these particles interact with the CMB or other background fields can confirm or constrain physical theories. There's also a small but fascinating possibility. Could these particles be one avenue by which life's building blocks or other complex molecules are influenced? Probably not directly, given their rarity, but cosmic rays in general do induce mutations by spurring particle showers that reach the ground and sometimes alter DNA. The ultra-energetic ones are so few that they're not a significant factor for life on Earth. But it's interesting to note how even something as exotic as the oh my god particle connects to our planet. It struck our atmosphere, and its energy ultimately dispersed in the air above us, in a cascade of low-energy particles and a gentle glow of fluorescence. The pursuit of cosmic ray origins continues. Arrays are being upgraded, new detectors are being planned that might even be placed in space, or use large volumes of water or ice to detect secondary particles or related phenomena. Some researchers have even looked for flashes of light on the moon caused by cosmic ray impacts as a way to gather more data. There's a global community, eyes on the sky, not just for beautiful supernovas and distant galaxies, but for these invisible incoming torpedoes from the depths of space. Standing under the night sky, we might feel sheltered and small, but we're also connected to the vastness by this drizzle of atomic particles. Most of it is innocuous, even beneficial in a way. Some theories suggest cosmic rays might influence cloud formation and climate over eons. Yet the rare leviathans of the cosmic ray world hint at stupendous cosmic engines out there. Particles with energies beyond easy explanation continue to reach us, challenging what we think cosmic accelerators can do. Physics. Each one is a messenger from the universe's most violent realms, carrying a simple message. Somewhere, out there, a natural engine revved up to incredible power. As we ponder that message, we sense once more the theme of our exploration. Phenomena that defy understanding, yet beckon us to understand. We have listened to ghostly radio flashes and caught subatomic arrows shot from distant sources. Now, our path leads us to another realm of mystery. Not a thing or a particle speeding through space, but space itself and how it warps and dances under gravity's spell. The next mystery awaits in the bending of light and the warping of time, as massive objects act as cosmic lenses. It is time to step into the funhouse mirrors of the universe. Gravitational lensing, where the very fabric of space-time bends, creating optical illusions and sometimes warping the flow of time itself. We find ourselves gazing at a distant field of galaxies. Most shine serenely as pinpoints or smudges of light. But here and there, something odd appears. A single galaxy smeared into an arc, or a quasar duplicated into multiple identical points, as if reflected in a cosmic mirror. These are the handiwork of gravity, bending the path of light across the gulfs of space. Gravity, as Einstein revealed, is not just an invisible pull between masses. It is a curvature of space-time itself. Massive objects warp the space around them like a heavy ball on a trampoline, and light, though it travels straight locally, finds its path curved when it passes through this distorted space. The result is gravitational lensing, nature's own optical illusions, where distant objects can appear magnified, duplicated, or smeared out into rings and arcs by the gravity of intervening mass. This phenomenon was predicted by Einstein over a century ago, but it sounded like science fiction at the time. Who could imagine that space could act like a lens, bending beams of light? Yet in 1919, during a solar eclipse, astronomers observed starlight being deflected by the sun's gravity, a tiny but measurable shift that made headlines worldwide. It was one of the first proofs of general relativity. Starlight passing near the sun arrived at a slightly different position than it would have if space were flat, meaning the sun had curved the space around it. That was gravitational lensing in its simplest form. Over the decades since, we've found far more dramatic examples on cosmic scales. In 1979, a strange discovery was made in the constellation Ursa Major. Two quasars, the bright cores of distant galaxies, that looked eerily identical in color and brightness, sitting very close together in the sky. Eventually, astronomers realized these weren't twin objects at all, but one distant quasar whose light was being split into two images by the gravity of a massive galaxy positioned in front of it, directly along our line of sight. The intervening galaxy's gravity had bent the quasar's light into two channels around it, so by the time the light reached Earth, we saw two copies of the quasar. This was the first gravitational lens system confirmed. Nature's telescope, inadvertently at work. From that first discovery, we've now catalogued many such lenses. Some are breathtaking to behold. Photographs from the Hubble Space Telescope show giant arcs of light encircling galaxy clusters, which are actually the stretched images of background galaxies whose light has been distorted into rings. When a distant source, a near a massive lens, and the observer are aligned just right, the background source can appear as a perfect circle of light around the lens, the famous Einstein ring. In other cases, slight misalignments create multiple discrete images. One of the most iconic is the Einstein cross, a single quasar in Pegasus, so perfectly lensed by a foreground galaxy's gravity that it appears as four quasars arranged in a cross-like pattern around the galaxy's center. Seeing it through a telescope is almost eerie. Four identical-looking lights, each one the same quasar, whose true position is directly behind the central galaxy that's lensing it. These phenomena are visual proof that space can warp like a funhouse mirror, producing mirages on a cosmic scale. Gravitational lensing not only creates pretty oddities in the sky, it also serves as a powerful tool for astronomers. Those distorted images can be analysed to reveal the mass of the lensing object, even if that mass is partly or wholly invisible, as is often the case. Much of the lensing mass is dark matter we can't see directly. By studying many lensed systems, scientists map out where dark matter resides in galaxies and clusters, since the amount of bending depends on the gravity of the lens. Lensing has shown, for instance, that galaxy clusters have huge halos of dark matter, far more mass than the visible galaxies alone, which is one way we know dark matter exists. It also allows us to see farther than we otherwise could. A massive cluster lens can magnify the light of a much more distant galaxy behind it, acting like a natural telescope that lets us observe some of the earliest galaxies in the universe that would normally be too faint. In recent years, astronomers have even found lensed images of objects like supernovae, and remarkably, multiple appearances of the same supernova at different times. This is where gravitational lensing truly earns the nickname time warp. Consider this astonishing consequence. If light from a distant exploding star, a supernova, is lensed by a massive cluster of galaxies, the light can take multiple paths around the cluster to reach us. Some paths are a bit longer than others, or pass through different depths of the cluster's gravitational well, causing those beams of light to travel on a different schedule. We might see the supernova's flash via one route first. Then, weeks or years later, we might see it again via a longer route, essentially a replay of the same event from another path. This isn't just theory, it has been observed. In one case, astronomers saw a distant supernova 3 times, in 3 separate images, lensed by a galaxy cluster, each image showing the supernova at a different stage of its explosion. They predicted that a fourth image of that supernova would appear in the coming decades as the last light takes the longest path around the cluster and reaches Earth later. It's as though the universe offered a natural time machine or a delayed broadcast. By measuring the delays between these multiple appearances, scientists can glean an incredible amount of information, not only about the lensing cluster's mass distribution, but even about the expansion rate of the universe itself. This technique, known as time delay cosmography, uses those differences in arrival time to help refine estimates of the Hubble constant, the rate of cosmic expansion. To a traveller in that distant part of space, the supernova happened once. But to us, gravity's bending of space-time made one event arrive numerous times. This gravitational time dilation, or time warp, is a mind-bending concept. Time and space are so interwoven that a massive object can literally give us a delayed view of events behind it. We can stand here on Earth and know that in 20 years, if predictions hold, the sky will light up with the echo of a supernova that already happened, but whose last photons are still on their roundabout way to us. It's both eerie and wonderful, as if the universe enjoys storytelling, repeating a line for dramatic effect long after the line was first spoken. Gravitational lensing beautifully illustrates how strange and non-intuitive the universe can be. Space can curve. Light can travel on bent paths. Looking out into space, we must always remember we're looking through a funhouse mirror of sorts, especially near massive objects. Even the images of the most distant galaxies we see are often subtly distorted by the gravity of intervening matter all along the line of sight, a phenomenon known as weak lensing that statisticians tease out from large data sets. On the largest scales, this leads to cosmic shear, where distant galaxy shapes appear slightly stretched due to all the cumulative gravitational lensing by clumps of dark matter in the universe. By measuring this shear across the sky, scientists can map the large-scale distribution of dark matter and understand how structure has evolved over cosmic time. For our narrative, however, the strangeness of gravitational lensing lies in its visual and temporal trickery. Imagine gazing at a massive cluster of galaxies through a powerful telescope. You notice a faint smudge of blue light curving around the cluster's center. That blue smudge is not part of the cluster at all. It's the image of a galaxy, billions of light years beyond it, wrapped into a curve by space-time. Or imagine studying a bright quasar and realizing it has an identical twin nearby, with absolutely the same properties, down to subtle flickers. Only by long investigation do you confirm it's one quasar, mirrored by gravity. The universe has given us a natural kaleidoscope, and beyond the aesthetic marvel, each lens is a deep well of information. The time delays between multiple images depend on both the cosmic distances and the curvature of space. Offering a way to measure those distances. Thus, gravitational lenses have become tools to probe cosmic expansion and even to weigh the universe's content. But even as we use them for science, we can pause to appreciate the sheer wonder. Space acting like a lens, gravity as an artist distorting light. Stand in one of those distant galaxies being lensed, and you'd see perhaps multiple images of the Milky Way or bizarre optical effects looking outward. From our vantage, it's a reminder that the straight lines and Euclidean geometry we take for granted in daily life give way to something far more fluid on cosmic scales. Space can stretch and bend. The shortest path for light is not always straight to our eyes. It must curve along the contours of space-time shaped by mass. One can't help but sense a slight eeriness when contemplating gravitational lensing. These hovering phantom images in the sky hint at the presence of something massive and often unseen, like dark matter, that is bending the light. We see the effect of an object's gravity, even if we don't see the object itself clearly. It's like seeing only a distortion in a pane of glass, and deducing an invisible finger is pressing on it. In fact, gravitational lensing has revealed entire galaxies hidden behind the glare of nearer objects, and even helped discover planets around distant stars via a related effect called microlensing, where a star's brief lensing of a background star can betray an orbiting planet by adding a blip in the lensing light curve. The phenomena of gravitational lensing and time warps show us that our intuitive sense of space and time is limited. We've learned that not only can space curve, but time can be offset. One path for light might take longer than another, so we literally see events out of order. In extreme cases, like near a black hole, time itself runs slower, deep in the gravitational well, relative to an outside observer. Lensing doesn't usually create significant time dilation of the signal, beyond the travel time difference. But it's part of the whole picture of general relativity that time and space are malleable. As we leave the realm of gravitational mirages, we carry with us the sense that the universe is a layered tapestry of effects, some straightforward, many subtle and strange. We've heard cosmic whispers and caught cosmic bullets. We've seen space bend light like a conjurer bending spoons. What could be left to astonish us? Plenty, it turns out. Our next stop lies not with ephemeral signals or distortions of view, but with a titanic mystery at the grandest scales of structure, an enigmatic gravitational pull that seems to be drawing entire galaxies towards some unseen mass. We now venture toward the Great Attractor, a gravity anomaly of immense scale that tugs at our Milky Way and countless other galaxies, as if luring them toward an unseen cosmic rendezvous. Far beyond our own galactic neighborhood, across a region of hundreds of millions of light years, galaxies are not just flying apart with the expansion of the universe. They carry peculiar motions on top of that expansion, as if being gently pulled in a particular direction. Our Milky Way, for instance, is cruising through space at roughly 600 kilometers per second, over 2 million kilometers per hour, relative to the cosmic microwave background rest frame, in a particular direction, roughly toward the constellation Centaurus. This movement is shared by our neighboring galaxies and clusters. We and the galaxies of the Virgo supercluster are all being drawn towards something. That something has been dubbed the Great Attractor, because it appears to be a gravitational focal point, influencing a whole region of the universe, hundreds of millions of light years across. It's as if we live on a gentle slope of a landscape, and everything in our vicinity is rolling downhill toward a valley, but a valley we cannot fully see. The discovery of the Great Attractor arose from careful maps of galaxy motions. In the 1970s and 1980s, astronomers measuring galaxy redshifts, the speeds at which galaxies recede due to cosmic expansion, noticed slight irregularities. Galaxies in one part of the sky had residual blue shifts or smaller redshifts than expected, indicating they were moving toward a certain region, while those in the opposite part of the sky were lagging as if pulled backwards. Combining many measurements, a picture emerged that our local group of galaxies, the Virgo cluster, and other clusters around, are all trending toward a point in the southern sky, in the direction of Centaurus, roughly 200 million light-years away. This point, the Great Attractor, appeared to have the gravitational pull equivalent to a concentration of mass, millions of billions, times that of the Sun, on the order of 10^16 suns. That's the mass of a large cluster of galaxies, or even a small supercluster. Yet, when we look directly in that direction, with optical telescopes, we saw very little. The zone toward Centaurus lies behind the dense band of the Milky Way, what we call the zone of avoidance, where our own galaxy's stars and dust obscure the view beyond. The Great Attractor, tantalizingly, is hiding behind the glare and dust of the Milky Way's plane, making it extremely challenging to observe in visible light. Astronomers didn't give up, of course. They turned to other means, X-ray observatories and radio surveys that can penetrate the dust. And gradually, the veil began to lift. In the direction of the Great Attractor, about 200 million light-years away, an X-ray survey revealed a massive cluster of galaxies, now known as the Norma Cluster, Abell 3627. This cluster is packed with large, old galaxies, many of them colliding or interacting, and it radiates strongly in X-rays from the hot gas pervading it. It seemed to sit right near the calculated central region of the Great Attractor. The Norma Cluster alone has a tremendous mass, perhaps on the order of 10 or 15 solar masses, enough to be a major component of the Great Attractor's pull. Around it, other groups and clusters of galaxies in that hidden zone have been identified through radio and infrared surveys. So what once was an unseen mystery is now partly charted territory. We know there's a massive collection of galaxies there, and indeed their gravity is tugging on us. However, the story doesn't end with, "We found a big cluster." The more we mapped, the more we realized the Great Attractor might itself be just a part of an even larger structure. In the 1990s and 2000s, attention shifted further outward to an enormous conglomeration of galaxy clusters called the Shapley Supercluster, located roughly 500 million light-years away in the same general direction. The Shapley Supercluster is the largest concentration of galaxies in our nearby universe that we know of, an awe-inspiring node of hundreds of clusters. It's so massive that it might be the real gravitational heavyweight steering motions in our sector of space. It's as if the Great Attractor is a nearer hill, but beyond it lies a mountain, Shapley, which is the ultimate pull. In fact, measurements suggest that the Great Attractor itself may be moving towards the Shapley Supercluster. Our Milky Way, local groups, the Virgo Cluster, the Norma Cluster, Great Attractor region, all of these are streaming toward the larger Shapley concentration. The Great Attractor is like a waypoint, a local valley in the cosmic landscape, but beyond it is an even deeper valley, drawing everything in. Despite these revelations, the term Great Attractor remains a fitting one when describing our local region's peculiar motion. It conjures an image of some massive, unseen thing dragging us in, a bit menacing, a bit mysterious. In truth, it's not a single object like a monster galaxy or black hole. No, it's definitely not a single black hole sucking us in or anything apocalyptic like that. It's the collective gravity of tens of thousands of galaxies, plus a huge amount of dark matter, centered around the Norma Cluster and its environs. It's a gradual flow, not a violent crash. Galaxies aren't zooming like rockets into a drain. They're ambling along a gentle gravitational gradient that over hundreds of millions of years will tend to merge superclusters together. From our perspective, we can't feel this motion, but we can measure it against the reference of the CMB, or distant quasars. One might wonder, what will happen in the far future? If we and our neighbor galaxies are being pulled toward the Great Attractor, will we all end up there? Current understanding of cosmic expansion suggests that unless the overdensity is enormous, the overall expansion of the universe might still dominate on the largest scales. It's a battle between local gravity and global expansion. The Great Attractor region, and Shapley beyond it, are indeed overdense enough that they will eventually pull in their surrounding galaxies, likely merging Virgo, Norma, and other groups into one huge supercluster eventually. Some scientists have redefined our local supercluster of galaxies with this in mind. Rather than the Virgo supercluster, they propose a bigger concept called Laniakea, a Hawaiian word meaning immeasurable heaven, as the supercluster that includes the Milky Way and is centered on the Great Attractors region. In this picture, Laniakea is an enormous basin of attraction containing about 100,000 galaxies, all linked by gravity, such that flows of galaxies converge toward the Great Attractor at the center. Our Milky Way's cosmic address would thus be Laniakea Supercluster, Great Attractor, Central Region. It's poetic. We belong to immeasurable heaven, gradually drifting along with its currents. The Great Attractor captured the popular imagination because it sounds like a literal attractor, some giant magnet in space. The reality is both more prosaic and more complex. It's a busy, hidden region of clustered galaxies and dark matter, and part of a vast network of structures. But from our view, obscured by the Milky Way's plane, it long remained a puzzle. Even today, fully mapping it is difficult. We have to rely on indirect observations and multi-wavelength astronomy. Each galaxy found behind the Milky Way is like finding a coin on a beach under the sand. Painstaking work, often done one galaxy at a time with radio surveys, which can detect the neutral hydrogen emissions from galaxies through the dust. Bit by bit, the landscape of the Great Attractor is revealed. A cluster here, a filament of galaxies there. One intriguing aspect of the Great Attractor mystery is how it demonstrated the presence of massive structures that aren't obvious just from looking at galaxy maps. It reminds us that much of the universe's mass is dark, and that motions of galaxies can expose hidden mass distributions. Those peculiar velocities, deviations from pure Hubble expansion, like clues in a detective story, led us to infer the existence of a massive suspect behind the curtain of the Milky Way. When we finally caught a glimpse via X-rays, the suspect was indeed there, big and imposing. Standing back, what does this mean for us? It means our galaxy is part of a larger gravitational dance. The Milky Way and its neighbors are not isolated. We are involved in a slow-motion drift toward a distant destination. But fear not. This is not a collision course to doom. It's a gentle settling over a timescale so long, billions of years, that by the time any dramatic meeting happens, the landscape of the universe will have changed due to expansion and maybe even cosmic acceleration, dark energy. In fact, dark energy, the accelerated expansion of the universe, may eventually win out and pull even the Great Attractor's realm away from us faster than gravity can overcome, meaning we might never actually reach it. Alternatively, if the local gravity is high enough, our region might eventually separate from the Hubble flow and collapse into one big supercluster. Those are scenarios for the far future. But in the here and now, the Great Attractor remains an important reminder that not everything in the universe is readily visible or understood. Even something that influences millions of galaxies can hide behind a veil, in this case the Milky Way's disk, and elude easy observation. It took decades of effort to piece together what it is. And some questions remain. For instance, is the concept of the Great Attractor as a singular entity still useful now that we know about Shapley? Many astronomers today would say the Shapley supercluster is the real heavy pull, and what we called the Great Attractor was a regional effect, part of a larger flow toward Shapley. So in a way, the mystery evolved. We solved one riddle, the Norma cluster and associated mass, only to find a bigger attractor beyond. There is always another layer, a common theme in cosmic mysteries. Having delved into a hidden concentration of mass, we now widen our perspective to the largest canvas of all, the entire universe. And even there, in the afterglow of the Big Bang itself, we find puzzling features. One of these has been a subject of intense interest and speculation: a curious cold spot in the cosmic microwave background, a region colder than expected and hard to explain with standard theories. It's time to examine this subtle anomaly in the very map of the infant universe and explore why it has left cosmologists scratching their heads and contemplating ideas as profound as the possibility of other universes. In the 1960s, when Arno Penzias and Robert Wilson discovered the cosmic microwave background, CMB, the faint afterglow of the Big Bang, it was remarkably uniform. It's a nearly perfect background temperature that fills all of space, about 2.73 Kelvin above absolute zero. But it's not perfectly smooth. It has tiny variations, like faint freckles on an otherwise even canvas. These temperature fluctuations, typically only tens of millionths of a degree, correspond to the seeds of what would become galaxies and clusters, regions that were slightly denser or thinner in the early universe. By mapping them, satellites like COBE, WMAP, and Planck have given us a baby picture of the cosmos. And in that baby picture, scientists found an odd blemish: the CMB cold spot. Located in the direction of the constellation Eridanus, this patch of sky, spanning a few degrees, is unusually cold, significantly more so than typical variations. How cold is unusually cold? The average CMB temperature is 2.725 K, and typical tiny fluctuations might make some spots a few tens of microkelvins hotter or colder than that mean. The cold spot, however, is about 70 microkelvins, 0.0007 K, colder than the average. In its very coldest part, it reaches roughly 140 microkelvins below the mean. That might not sound like much, fractions of a thousandth of a degree, but in the context of CMB anomalies, it's a whopper. Moreover, it's spread across a region about 5 degrees across the sky. To visualize that, 5 degrees is about 10 times the width of the full moon. So this cold region is enormous in angular size, covering a sizable chunk of the sky. The cold spot stands out even to the eye on full-sky CMB maps. If you compress the whole sphere of the sky into an oval, it's noticeably down and to the right in the southern hemisphere, a big blue patch amidst the mottled pattern of hotter, red, and colder, blue spots. When the cold spot was first identified in the WMAP satellite data in the early 2000s, cosmologists took notice. The statistical analyses suggested that having such a large, deep, cold area was unlikely, though not impossible, under the simplest inflationary Big Bang models, where the fluctuations are largely random, Gaussian, with a certain spectrum. One calculation put the odds at around 1 or 2% that a random map consistent with our best fit cosmological model would have a feature as extreme as the cold spot. In other words, it's an outlier, not utterly beyond the realm of chance, but rare enough to raise eyebrows. It compelled scientists to ask, is this just a fluke, or is something interesting going on? First things first. Could it be an artifact? The Planck satellite, with better resolution and sensitivity, also observed the cold spot, confirming it's real and not some quirk of WMAP or unaccounted noise. It wasn't interference or instrument error or a galactic foreground issue. It appears to be a bona fide feature of the CMB sky. So, assuming it's real, how could it arise? One straightforward explanation is the one scientists favor for any anomaly. Perhaps just dumb luck. After all, with billions of possible patches of sky, somewhere there's bound to be an odd one. Maybe we just got super unlucky and got a cold spot by random chance, as some have put it. While the probability is low probability events do happen. If you have a 1% chance event and you only get to see one universe, sometimes you might just be that 1%. It wouldn't invalidate the Big Bang theory or anything drastic. It would just be an interesting statistical fluke. However, scientists are paid to be curious, so they've explored other possibilities with gusto. One leading hypothesis involves a supervoid, an unusually empty region of space between us and that part of the CMB. Here's how that works. The CMB's photons have been travelling for 13.8 billion years towards us, and along the way, they can be affected by large structures. If a photon passes through a dense cluster, it might gain a bit of energy falling in and lose it climbing out. But in a perfectly symmetric situation, it ends up about the same. If it passes through a big void, something interesting can happen. Early on, as the photon enters the void is smaller, and the photon gains a little energy descending into a shallower gravitational potential. But as it leaves, the void may have expanded. Voids grow emptier and larger as the universe expands. So the climb out is from a deeper well than the fall in, and the photon can lose more energy than it gained. The result? The photon comes out a bit less energetic, which means cooler when we see it in the CMB. This is a variant of the integrated Sachs-Wolf effect, or Rees-Sciama effect, for an evolving gravitational potential. So, a large void along the line of sight could imprint a cold spot on the CMB by stealing some energy from the photons. If the Eridanus direction had an enormous void, perhaps the largest known void in the universe, that could explain the cold spot's existence. Researchers went looking, and indeed found some evidence of a shallower density of galaxies in that region of the sky. Surveys indicated fewer galaxies than average, hinting at a void perhaps hundreds of millions of light-years across, at a few billion light-years away. Some headline even proclaimed the largest void had been found. However, this explanation is not universally accepted. Some studies did identify an absence of radio galaxies in that direction, consistent with a void, while others argue any void present is not large or deep enough to cause the full effect. There's debate. One team's supervoid is another team's nothing special there. And even a very large void might only account for part of the temperature drop. Calculations suggest a void that could cause a 70 microkelvin cold spot would have to be extraordinarily vast, on the order of 1 billion light-years across, and extremely empty, which pushes the limits of plausibility in standard cosmology. Given the difficulty of the void explanation, other exotic ideas have been floated. One of the most fascinating, though highly speculative, is the notion that the cold spot could be evidence of something beyond our universe's standard structure, perhaps a collision with another universe. In some models of inflation, the rapid expansion in the early universe, our observable universe might be one bubble in a frothy multiverse. If another bubble universe had once upon a time bumped into ours, it might have left a faint imprint on the CMB, maybe an area of slightly different temperature or statistical properties. Some theorists proposed that the cold spot could be such a bruise from a collision with a neighbouring universe. It's a mind-boggling idea, that an entire other reality brushed against ours in the primordial epoch, and all we see now is a subtle cool patch in the sky as a result. So far, this remains highly conjectural. It's hard to devise a test for it, though people have tried to see if the cold spot has unusual polarization or shape that might hint at something non-standard. Even those proposing the multiverse collision idea admit it doesn't perfectly explain the cold spot either. It's just one of those intriguing possibilities that get bandied about when conventional explanations falter. Another proposal involves cosmic textures, which are defects in the fabric of the early universe's fields that could arise during symmetry-breaking phase transitions, analogous to cracks forming in ice as water freezes. A texture could cause a one-time distortion in the CMB as it decays, potentially making a cold or hot spot. In 2007, a study in Science suggested the cold spot might be well fit by the hypothesis of a cosmic texture, rather than just Gaussian random fluctuations. If a texture were the cause, it would be a sign of new physics in the early universe, like indicating the type of symmetry breaking that occurred. But like the multiverse idea, it's speculative and hard to confirm. Subsequent analyses have not decisively favored the texture interpretation. It remains one of several possibilities. For now, the cold spot endures as an enigma. Perhaps further data, say, even more precise maps of the CMB or larger-scale structure surveys, will clarify whether there's an associated void or other feature. So far, the consensus, though not unanimity, is that the cold spot might just be a rare statistical fluke. One possible in the 1 in 100 range given our universe's initial conditions, but not requiring new physics. Still, it's so tempting to explore the alternatives, because if any proved true, they'd have profound implications, a window into a multiverse, or evidence of new forces shaping the early cosmos. Regardless of the cause, the cold spot has inspired the public and scientists alike to ponder grand possibilities. It's often brought up with a sense of mystery. Could it be a sign of another universe? For many, it exemplifies how even the most subtle details in nature's grandest canvas can lead us to deep questions. After all, this spot is just a few microkelvins colder. That's a tiny fraction difference in an already cold 2.7 K background. Yet it has opened debates that touch on the very origin and perhaps plurality of universes. It shows the precision of modern cosmology. We're no longer just observing that the CMB exists, we're scrutinizing its freckles and wondering why one freckle is a bit bigger and darker. Standing under the night sky, you won't see the cold spot with your eyes. It's only in the microwave maps. But if you could, it might appear as a very faint, wide patch, slightly cooler than its surroundings in the all-sky glow. There's no impact on our local environment from it. It's a historical record. But in that record lies encoded the story of how matter clumped, how our universe expanded, and possibly hints of what lies beyond. The cold spot sits out there, 13 billion years in the past, quietly challenging our assumption that the early universe's fluctuations were perfectly random draws from a simple distribution. Whether it is an artifact of chance or a clue to something profound, the cold spot has achieved a kind of fame in cosmology circles. We've measured it, debated it, and even joked about it. Maybe someone left the fridge open in that part of the universe. It remains one of the few major CMB anomalies not fully understood, along with a few others like perhaps some alignment of low-order multipoles, the so-called axis of evil, that some have noted. But it's by far the most talked about one. In the spirit of our cosmic journey, the cold spot story teaches a humble lesson. Even in what we consider the most uniform, well-understood backdrop, the glow of creation itself, there can lurk the unexpected. The universe, at every scale, presents phenomena that defy complete understanding, beckoning us to dig deeper. From fast radio bursts and high-energy cosmic rays, to warped light and hidden mass, and now to strange imprints on the cosmic dawn's light, we see time and again that each mystery solved often leads to new questions. Our exploration of the universe's strangest secrets has carried us across an immense range of scales and concepts. We've listened to ephemeral signals that hint at star-born exotica, We've chased atomic particles flying solo with the power of macroscopic objects. We've marveled at gravity's ability to sculpt light and time. We've sensed the pull of a hidden concentration of mass drawing us in, and we've confronted a puzzling cold blemish on the very face of the early cosmos. Each topic stands on its own as a deep puzzle. Together, they paint a picture of a universe that is rich, surprising, and not easily reduced to simple laws without remnants of the unexplained. As we conclude this chapter of our journey, we remain suspended in that delightful state of wonder. The cosmos clearly has more up its sleeve, phenomena yet undiscovered, puzzles yet unsolved. Our adventure is not over. In fact, in the grand scheme, we may only have scratched the surface of cosmic mystery. The beauty of science is that it is an ongoing story, and the universe seems inexhaustible in providing plot twists. Gently and humbly, we step forward, ready for the next part of our voyage, knowing that beyond the horizon of current knowledge, even stranger secrets await, quietly illuminating the night and awaiting the curious mind to find them.